So, man, I'll take some water. Okay.
Yeah. Yeah, definitely. Definitely.
Hello, Dr. Miranda.
Hello.
Yes, I just wanted to confirm a small thing. Your name is Pericles, right?
Yes, Pericles Miranda.
I hope I'm audible and visible. Hello. Okay, thank you, sir. Hello and good morning to all. The only true wisdom is in knowing that you know nothing. Starting the day with this profound saying by Greek philosopher Socrates, a very warm welcome to all the delegates present here on the third day of Global Conference on Artificial Intelligence and Applications, GCAIA 2021, organized by University of Engineering and Management, Jaipur. My name is Professor Shatabdi Basu from Department of Computer Science and Engineering, and I will be your host for today's session. The aim of this conference is to promote dialogue between scientists, researchers, engineers, corporates, and scholar students to mitigate the gap between academia, industry, and governmental ethics. This motivation will be fostered through keynote speeches and oral presentations by eminent researchers in relevant fields. The platform of GCAIA will bring regional and international concerns for the discussion on recent advances in modern computational intelligence. The first research keynote speech of the day would be delivered by Dr. Pericles Miranda, adjunct professor at the Federal Rural University of Pernambuco, Brazil, and chief scientist at the AI Box Lab. Dr. Miranda has extensive experience in the field of computer science with an emphasis on artificial intelligence, working mainly on topics related to automated machine learning, AutoML, supervised learning, meta-heuristic, and hyper-heuristic algorithms. Dr. Miranda, we welcome you to GCAIA 2021, and I request you to deliver your address on AutoML, past, present, and future. It's over to you, sir.
Thank you. It's a pleasure to be here. Thank you very much for the invitation. Can you hear me well and see me well?
Yes, sir.
Yes, I'll share my screen, okay?
Okay, sir. Okay, sir. Please share.
Please let me know if you can see the presentation.
Yeah, definitely. It's absolutely visible. It's absolutely visible.
Okay, thank you. Again, thank you very much for the invitation. It's a pleasure to participate of the event. I'm Pericles Miranda, and I'm going to talk about the subject AutoML, past, present, and future. And before I start, I'd like to introduce myself. I'm from Recife, Pernambuco. Pernambuco is a state from the northeast of Brazil. My PhD is in computer science with expertise in AI. I hold the role of professor at the UFRPE, Federal University in Pernambuco, and also hold the role of coordinator at the AI Box Lab. This lab focuses on the development of intelligent solutions for the industry. And I've been working with AutoML since 2011. I brought some pictures from my city. I don't know if you already had the opportunity to come here. It's a city surrounded by the sea. It's a historical city, very beautiful. I like so much to live here. And all of you are invited to, when you can come here, it will be a pleasure to receive you, to have you here. Okay, here is the outline of the presentation. I will introduce the motivation of using AutoML. We are gonna talk about automated machine learning itself. I will contrast the human process against the AutoML process, right? Next, we will present the timeline of the AutoML evolution. After that, some open issues, some future trends, and some conclusions. Okay, in 1997, Tom Mitchell said, ever since computers were invented, we have wondered whether they might be made to learn. If we could understand how to program them to learn, to improve automatically with experience, the impact would be dramatic. This sentence said by Mitchell inspired many researchers. And machine learning since then have deeply rooted in our everyday life. Machine learning techniques have evolved so much. And now we can see many applications in the recommendation of products in different sites, face and handwriting recognition in cell phones. Definitely machine learning is in our everyday life. And besides that, ML has gained relevant achievements. We have the examples of AlphaGo that defeated human champion the game. ResNet surpassed human performance in image recognition. And we also have the example of Microsoft's speech system that approximated the human level in speech transcription. However, these successful applications of machine learning, they are very far from fully automated, right? What's the current scenario? The scenario is humans are heavily involved in every aspect of machine learning. When we work with machine learning, we interact with a data pipeline. where the output is the machine learning deployment. In this pipeline, we have some steps that the human is very involved, such as feature engineering, model selection, algorithm selection, for example. And the problem is, if we involve humans in this process, the problem is that the experts are rare and the success comes at a great price, right? So our intention in this presentation is to present to you an alternative to answer this question: how to make machine learning techniques easier to apply and reduce the demand for experienced human experts. So our idea is to make the pipeline process easier and focus the human activities on business, on strategic activities. And the core of the pipeline be the responsibility of the computer. So automated machine learning, the idea is to be an alternative for this question, right? And this term emerged as a new sub-area in machine learning, right? And the idea is to enable faster deployment of machine learning solutions across organizations, efficiently validate and benchmark the performance of the deployed solutions, and also make experts focus more on problems with more application and business values. So the idea, as I said, is to allocate humans in more strategic activities and automatize the some steps to make the process faster and easier, right? Here we can see the pipeline of data, right? Initially, we have the problem definition, data collection, feature engineering, model selection, algorithm selection, evaluation, and deployment. As we can see, the humans, the experts, were responsible for all the steps, right? However, this process is very, we have many challenges during this process. And most of the steps are very expensive, very cost. So the idea is to isolate the core of this process, the feature engineering, model selection, algorithm selection, and evaluation. This core will be the responsibility of the AutoML system, and the expert will be responsible for the problem definition, data collection, and deployment, strategic activities, right? So what's the idea of using AutoML in each core step? Well, in the feature engineering, the idea is to automatize and generate more informative features. So if we have a data collection with features that are not informative, the idea is to make aggregations, generations of more informative to help in the training process, for example. In the model selection step, the idea is to use the AutoML to choose proper classifiers and also find parameters without or few human assistance. In the algorithm selection, in this step, the idea is to select using meta-heuristics, for example, or generate using hyper-heuristics to learn and optimize algorithms, including their parameters, right? Balancing efficiency and performance. And considering the evaluation, At this step, the idea is to recommend evaluation metrics for models assessment. What are the evaluation metrics that can extract more information about the algorithm's performance? So that's the idea of the AutoML system at this step. And when we automatize these core steps, we can make machine learning applications more accessible for real-world usages. So the idea here is to make machine learning solutions more accessible, right, for common users. Okay, once we understood the idea of AutoML, what are the goals of this system? The first one is good performance. The idea is to achieve good generalization performance across various input data and learning tasks. The second one, less assistance from humans. So our idea is to identify configurations that can be automatically done for machine learning tools. And the last, high computational efficiency. It's very important to that the process can return a reasonable output considering a limited budget. Okay, so these are the three verticals of the AutoML goals. Okay, once we have talked about automated machine learning itself, now we need to compare the human process with the AutoML process. The human process is very simple, okay? This figure presents how the human process works. We need an expert. Let's suppose that we are considering an algorithm selection problem. So we have a pool of algorithms and we need to identify the most suitable one. So the idea is that the expert will try a configuration. This configuration will be evaluated considering a set of different metrics, evaluation metrics. And after that, we have a feedback. For example, let's suppose we are trying a specific configuration for the SVM, right? And the SVM with that configuration achieves 99% of accuracy. So this value is the feedback. When the expert have this feedback at hand, he or she is able to decide if it's enough or not. If it's not enough, the process continues. The search for a suitable configuration continues. If not, the process is stopped. The problem is that this process can be automatized, right? And allocate a human for that is not adequate. The human could be used for a more strategic activity. So what's the idea of using AutoML? The idea is to answer these two questions. First of all, what to automate? What do we want to automate, right? At this question, we need to set up the problem, to define the problem, trying to answer. This problem is a feature engineering problem, is a model selection problem, algorithm selection problem, neural architecture search. So at this step, our idea is to define what we want to automate. And this step will return as output for the next one. That is how to automate. At this side, we are interested in defining which techniques are adequate once we have the problem set up well defined, right? So we have different techniques, basic ones and experienced ones. The basic ones, we have genetic algorithms, for example, particle swarm optimization, optimization from samples, gradient descent, right? And we have also experienced techniques. These experienced techniques are meta-learning and transfer learning. These techniques are characterized by are techniques that have experiences from past experiments, right? So these techniques can help the search process, and they can be combined, right? So first of all, what we will want to automate. Second one, how to automate. Okay, besides that, we have to understand how the AutoML controller works. This controller is composed by two components: the optimizer component and the evaluator component. The optimizer component replaces the human, the expert, right? The optimizer receives as input the problem setup, right? That two questions. What to automate? The problem is feature engineering, model selection, algorithm selection. So the answer, the problem setup will define the search space. If we are dealing with algorithm selection, so our search space is composed by different algorithms, right? If we are considering hyperparameter selection, for example, our search space is composed by configurations. So the optimizer is used here to search suitable solutions. Each solution is provided for the evaluator. The evaluator is used to assess, to evaluate following an evaluation metric to measure the performance of that solution, right? And the feedback is given to the optimizer. And the optimizer will decide with if the optimization, the search continues or not, right? So that's the AutoML controller. And now we have an overview, a complete overview of all the process, right? Here we have the problem setup, as we discussed earlier. Here we have the techniques with the AutoML controller, right? And the first step is to define the problem setup. And the idea is to answer the following three questions. What learning process we want to focus on, right? What learning tools can be designed and used? What are resultant corresponding configurations, right? Answering these questions, we define the problem setup. This setup is provided as input for the optimizer and evaluator, right? Depending on the problem that we specified in the problem setup, we have to choose the adequate optimizers for the process. For example, if the problem is a combinatorial one or a continuous problem, we have to choose adequate algorithms for that. Well, in the optimizer, what questions are important to answer? What kind of search space can the optimizer operate on? As I told you, combinatorial, continuous. What kind of solution representation is required? So depending on the problem, we have to make these choices, right? Well, after that, the evaluator. So here we define which metrics we use to assess the solutions. So we have some questions that are important to answer. Can the technique provide fast evaluation? Can the technique provide accurate evaluation? right? What feedbacks need to be provided by the evaluator, okay? Well, it's important to say that this optimization process can be also combined with experienced techniques. As I told you, we can use meta-learning to guide the search. We can use transfer learning to provide prior knowledge about a domain for our process. So these experienced techniques can improve the performance and efficiency of our optimization process, right? So we can use them for that. Okay, we have discussed about AutoML. We have discussed about the comparison, the differences about the human process and the AutoML process. And now I will present to you the timeline of the AutoML evolution, okay? We can divide this evolution in three waves. We have the first wave from 2006 to 10, 2011 to 16, and 2017 to now. Well, I compiled some works that characterize well the first wave, okay? In the first wave, we can see some works from Escalante and Gorison, and these works characterize the wave, right? The pattern of the wave. And what's the pattern? The pattern is the usage of optimizers for the full model selection problem. It's important to say here that we can find some works that try to optimize the algorithm selection, the hyperparameter selection individually, but most of the works focused on the full model selection problem, where the idea was to find the best combination of data preprocessing, feature selection or extraction, and classification models, okay? And also the hyperparameters. In the second wave, this second wave is a little bit heterogeneous, right? We have different researches, okay, that focused in different ways, right? For example, we identified 6 possible ways in this second wave. The first way was the usage of Bayesian optimization and sequential model-based optimization for hyperparameter optimization and algorithm selection, right? So we identified in this second wave works that used these decisions, okay? And the idea was to estimate the relations between performance and the decision, hyperparameters or algorithm, right? Oops. The second research way in this wave was the development of AutoML tools, right? Like AutoWeka and AutoScaLearn. The third research that we identified was the use of multi-objective algorithms, mainly SMBO optimizers, for the problem of hyperparameter optimization and algorithm selection. The fourth research is related to the use of meta-learning for guiding the search process. So we have an optimizer. The meta-learning suggests promising solutions during the process, the optimization process. It's like an online optimization where the online recommendation is given by the meta-learning, right? It's another research that was identified in these moments. The fourth one is the teapot, right? It's an algorithm that uses genetic programming as optimizer. The idea is that the teapot was used for model selection, and each model in the optimization process was represented by a tree. So all the genetic operators like mutation and crossover used to change the structure, the tree structure. And as consequence, the model structure was changed also. So that's another kind of research that was identified in this moment. And finally, the usage of meta learning for parameter and algorithm selection. Okay. With the arise of deep learning methods from 2017 to now, we can identify many works that focused on the application of automated machine learning for deep learning, right? We can see the term neural architecture search. Okay, this term is very recent, okay, and it comes from the outstanding achievements of deep learning across many fields, right? And as deep learning is composed by different layers with different hyperparameters, each hyperparameter with different values, so the composition, the creation of a model is a complex task. So the neural architecture search focus on this focus to find the best architecture for a given problem, right? And besides that, we can also find reinforcement learning approaches and optimization algorithms to evolve deep learning architectures and parameters, considering mono, multi, and many objective functions, right? So in this last wave, the main focus, as I told you, is deep learning approaches, optimized deep learning approaches, okay? All right, now I'm gonna present to you some open issues, okay? As AutoML has an optimization structure, an optimization procedure, it's very interesting that all the process be transparent and reproducible, right? So it's very important that the AutoML infrastructure be explainable. So it's an open issue that has gained very attention in the last years, right? Another issue that is very important is regarding the feature engineering. Although feature engineering is the first step in that pipeline, the number of works is still limited, right? And most of the works consider tabular data. And with the rise of deep learning, where we have raw data, for example, text, images, and structured data, so the application of AutoML for non-tabular data is also an open issue. Well, besides that, as I told you, AutoML executes an optimization procedure. So when we mention optimization, at the same time, we are talking about computational cost. So it's very important to create an AutoML infrastructure that is able to be scalable to perform well in a large scale environment. Okay, so it's another open issue. And finally, it's very important to reuse information from the optimization process to avoid, for example, computational costs. If we can reuse this information from past experiments, why not to use this information in the optimization, okay? So an open issue is how to use meta learning and transfer learning in the AutoML process. Okay, so to conclude, we can see that AutoML aims at helping users with the design of machine learning systems. This approach is now a very established field with wide applicability in the data science era. AutoML has achieved a great progress in the optimization of hyperparameters of models, model type selection, and also full pipeline generation, right? And AutoML has made easier solutions for the design task, even for machine learning experts. So according to what we have seen along the years, this approach, right, has answered that first question that we made in the beginning of the presentation. The process became easier and faster, and have helped the experts in the process, right? So we have many open issues to tackle, but AutoML has shown promising results, right? I'd like again to thank you, thank the organizers, thank the event. It's a pleasure to be here. Me and my lab and I are open to talk to you about the subject, about research in general. And if you are interested to work with us, to collaborate with us, here is my email, pericles.miranda@ufrp.br. And I'm open for questions. Okay, thank you again.
Thank you, Dr. Miranda, for your informative presentation. I would now request the audience members to post their questions in the forum. So while we wait, I have a few questions from my side. So since we are automating the entire ML process from, say, model selection, parameter optimization, so does it mean that this introduction of AutoML will, remove the need for data scientists or people with ML skills in future? So is it like data scientists or ML scientists will become obsolete?
It's a good question. That's our fear, to be replaced by machines, right? But I think that our position in that pipeline is to investigate if the process is being fair, right? There is a very nice subject in AI called fairness. I don't know if you already heard about it, but it's very important that the models be explainable and fair. So I think that the data scientists and the machine learning experts, they have to be in an abstract level, observing how the pipeline is, how the pipeline is working, So not replaced, but in a more strategic, layer over the pipeline. Observing, analyzing, investigating the results, so in planning, right? But I think that years that we were spending energy coding or something like this, I think that these years, I think in the next 15 years, we are not doing these tasks anymore. I think we are in a superior layer, observing and trying to reduce the bias of the pipeline.
Okay, so that's a task cut out for future data scientists or ML scientists. And sir, I have another question. I think you already mentioned in open issues that transfer learning is an area which needs to be explored as far as AutoML is concerned. But are there any mature AutoML tools for meta learning?
Sorry, can you repeat, please?
I said that are there any AutoML tools for meta learning? I think Google and Microsoft have already these kind of tools, but for especially for meta learning, because this is also a new research area.
About the future.
Yes.
Of using meta learning for AutoML.
Yes. Are there any tools for that?
Alternative tools.
Yes.
Okay. Instead of using meta learning, you saying?
Yes, because we can. I mean, if meta learning process, if it can be automated as well. So we have some AutoML tools in the market, right? So any tool specific for meta learning or for transfer learning?
Oh, specific tools for that, for meta learning and transfer learning. Yes, personally, I've never been in touch with tools using meta learning. There are some that are public but not so robust, like Google tools or Microsoft tools. But there are some. I don't know if you already heard about Metal. It's an open source project that considers improves and develops meta learning approaches, right? But a consistent tool, I've never been in touch.
If there are any more questions from other audience members, thank you, sir, for answering my questions. Thank you.
Thank you.
The participants can also unmute themselves if they have any questions for Dr. Miranda.
If you prefer, you can write in the chat too.
Yes. And I think if they come up with any questions later on, they can also get in touch with you via email.
Perfect.
So we have this. So thank you, sir. We were honored to have you in this conference today. We have a small token of appreciation from the organizers of Gcaia. Please accept it with our sincere thanks. Shomin, sir.
Thank you. Yes, it's okay.
Okay. Thank you, sir, for gracing us with your presence.
Thank you. My pleasure.
For the next keynote speech session, it is my great honor to invite Dr. Saurav Malik. Dr. Malik is currently working as a postdoctoral fellow in Harvard University, Massachusetts, USA. He worked as a postdoctoral fellow in University of Texas Health Science Center at Houston and University of Miami Miller School of Medicine, Florida. A doctorate from Jadavpur University, Kolkata. Dr. Malik is also the recipient of Research Associateship from CSIR in 2017 and recipient of Emerging Researcher in Bioinformatics Award from BioClues and Bird Award Steering Committee in 2020. Dr. Malik has co-authored more than 60 research papers in various peer-reviewed international journals, conferences, and book chapters. He is the editor of many journals like Frontiers in Genetics, Archives of Medical Sciences. His research areas include data mining, computational biology, bioinformatics, biostatistics, and machine learning. Now I would request Dr. Malik to start his speech titled Understanding Bioinformatics and Computational Biology Through Machine Learning and Data Mining. It's over to you, sir.
Okay. Thank you, Shadabdi, for the introduction. So I'm starting. So my topic is understanding the bioinformatics and computational biology through machine learning and data mining. So this is the site map of today's talk. What is the introduction and why we choose the computational biology or bioinformatics, and as well as I also describe some basic concept of the biology, because there are a lot of persons who have rarely known the biological term. To start working in the computational biology or bioinformatics, you have to know the fundamental concept. What is actually going on biologically? Then we can apply any computational method like machine learning, deep learning, anything to that particular area.
and what is the problem, and that computational problem, that's we need to identify. Okay, and here I have also described some of my works and the basic framework. How can we apply? Because this is the vast things, and but the things we have to understand, we have to follow the flowcharts. How we apply, okay, and what is the output, and we get, and whether the output is compatible or relevant with the biological finding or not. It is not like that we randomly use and get some result. We forcefully say that we got accuracy more than 90%. That means it's very good. It may be bad in biological sense. So we have to understand both the things: how we computationally get the result, how it is good or bad, as well as how it is biologically relevant to the particular area. And last, I described some conclusion and future directions, as well as some other things. So main things, today's area, the main things, what is the problem? Main problem is handling the big data. That is the main things. And the big data may be the biological data or any other data. Okay, but if we see the biological data, then nowadays, there is a lot of funding is provided from many countries that is depending upon the cancer, or now the COVID is there. Lot of funding, many fundings. But the thing is that why we choose this computational biology? The thing is that we have to find out the best possible solutions by which it can reduce the time complexity. That's the main thing. And we can get the that is best possible features. So that means we have to find out the features, right? Here the features means here maybe we can say the biomolecule, maybe the genes, micro, anything, right? So it is called the features. So this the main thing is feature selection. Another is that feature extraction is also there, but for the biological perspective, we can't change the features. That is the thing. So feature extraction means we can produce a new features using the existing features. For the biological data, maybe I think that should not be do. We can't change the gene names or something. So here the biological prospective feature selection is the appropriate things. That means gene selections. And then classifications. Why classification? What type of classification? When you go to any medical store or any pathological center, suppose you want to make the blood test or anything, right? So thing is that you can get, maybe if you go there for biopsy, you can get some patients that means has a cancer, or some patients has not. So here you can understand there is a two kind of classes, right? So thing is that we have to find out the subset of the features, or maybe you can say the subset of genes by which we can easily classify the diseases. That means we can reduce the false positive rate as well as false negative rates. Okay, so this is our target. It is computational target. And another thing is the clustering. Clustering means here in the biological perspective, it is called the gene modules. Modules means groupings. So in some cases, that we can know, normally we can know the which one has a disease, which one not. That means if you go to actually the biological data is provided in form of a matrix. In the row side, the genes or features names are given, and in the column side, the patient's name is there, or maybe the cell names is there. So the thing is that when clustering is used, we have to find out the gene modules. That means that we have to find out the best possible dependent clusters or groups that should be maybe sometimes it's still cell wise, maybe in features wise. In maximum cases, feature wise clustering is required, because maybe in the biological data, the number of genes are very high, maybe 20,000, maybe 1 lakh or more than that. So we need to find out which is the best possible set of features which can easily and perfectly classify the diseases. That may be the set of 50, maybe the 100. And after when we get this set of features, then we can provide it to the lab for wet lab for testing it. How much it is true positive or false positive can be found by the wet lab test. Okay, and there is other things are also there. We can make the pathway analysis on anything. But the main thing is that you can do the lab testing will happen after getting the results of the in computational perspective.
So main thing is the that means dimension reduction things in computational that means scenario. So now I'm going to the basic concept with the biology, biological term used here. We all know that DNA is there, deoxyribonucleic acid, and when it is transferred to the RNA, ribonucleic acid, this process is called the transcription. And when from the RNA and protein is made, then it is called the translation. And sometimes the DNA to DNA, when it is formed, clone is formed, then it is called replication. So here we all know about the genes, right? We all know about the vaccines, right? So we also take the medicines, right? So thing is that we normally, in normal perspective, we work on the protein levels, right? And the vaccines which are provided, that is the RNA vaccines, not the DNA vaccines, right? Which you have to understand, right? Any type of COVID vaccines, maybe the anything. They are mainly the RNA vaccines, not the DNA vaccines, because the DNA is very difficult to change it. Okay, RNA, I think less, it can change. That means less. Okay, it can change more, I think. And in the protein level, it will change. That means more than these other two. Okay, so and the genes means it is the part of the RNA. Okay, so you can say that there is a lot of RNA is there, tRNA. RNA means ribosomal RNA, and also there is a lot of RNAs. And another one type of RNA is there, messenger RNA, which is called mRNA, and that is also called the genes, right? So we have to understand that we are in the RNA level. That means if we take the vaccines, right? And when we go to the DNA level, then it will be better. So in future, if any vaccine is made, depending upon the DNA level, then obviously it will work 100% or maybe near to the 100%. But if you can see, all the vaccines are working maybe 70%, 90%, 80%. That is the reason. RNA can change. Okay. So this is the basic things you can understand. And we work on the features or genes. That means the RNAs. We working on the RNAs. And any type of drug we are taking, medicines, that is in the protein level, right? So this is the another part of the things. We already told the RNA, mRNA, that means genes, and another thing is there which is called the microRNA, and another is link RNA. What is the microRNA? The genes, we know that it can carry the biological information from one parent to child, but microRNA is it can't, that means provide the genetic codes. It is, you can say, it is the activator or influencer. It can influence on the genes on which it targets. Okay, that means suppose this microRNA targets on one gene. That means it tries to suppress the genes. That means if the expression level or intensity level of the genes is higher, then if any microRNA will just targets that genes, it try to minimize the expression level, right? So we have to understand the relationship between the expression of microRNA and genes are inverse. And link RNA, another thing is that it is also non-coding RNA, but it cannot, that means for the microRNA it can only suppress, but for link RNA it can suppress, and as well as it can also activate or to make the expression higher. It depends, right? And also this link RNA, nowadays one of the most important link RNA is H90. So you can see in the computational approach. So what is the main finding from the computer science perspective? We have to understand from these things, we can make some motive finding. Motive means we can say the clusters of 3 or 4 biomolecules together, which has a dependency, right? Maybe here the one is microRNA, one is link RNA, another you get things is genes, and another thing is transcription factors is there. So you can get 3, 4 biomolecules, and depending upon their dependence, we can make some that means modules, or we can say the motifs. Okay, that is what is important because we get all the factors, so it is very useful to find out the disease, right? So why we choose the computational biology and bioinformatics? So we know the computational biology means we have to find out the computations, that means the mathematical things, and then biology. Okay, and you can know that these bioinformatics can combine the multiple. That means it is the multidisciplinary subject. You can say it can combine the biology, computer science, information technology, mathematics, and statistics. In statistics, you can say the biostatistics, and then try to interpret in their own way. Okay, and I mainly here try to focus on the feature selection because it is the main things of the computer science. Okay, the feature selection. Why we take the features? Actually, feature selection is the process. What I already told, it is set of features by which we can effectively distinguish between the different classes or clusters. Most of the features in biological data are irrelevant. There may be some noise or anything. So we have to find out the best possible features which does not have noise or very less noise, and which can provide the that is best possible robust model to define or classify the disease. Okay. So there are so this is one thing, and this is the main. These are partial things I'm not describing here. So to know the that means feature selection. There are different kinds of feature selection. One type of feature selection you can say the statistical feature selection, that is called hypothesis test. It includes the t-test lemma, which can find out the features in the statistical by that means comparing between the two groups of patients and how vary their expression levels from each other, and whether it is significant or not, it can provide some p-value. So the thing is that, so that is one type of feature selection, but in the computer science, the main one kind of feature selection is the mutual
information-based feature selection. That is also called the supervised feature selections. So to know the mutual information, we have to know the entropy. So entropy means, what is the entropy? The uncertainty. If we may, that is toss a coin, then there is a two possibilities. One is head, another is tail, right? So the here the uncertainty of getting any event, maybe the tail, is 0.58, right? So this is the entropy. And the best possible entropy is Shannon entropy. Okay, this is a well-known thing. This is the that is mathematical piece. I'm not going to that portions. And now I'm going to the mutual information. This is very important. What is mutual information? Mutual information is basically it can share, that is the shared information between the two variables. Okay, that means the information which is shared by both the variables. Okay. The mutual information, there is a lot of property. Okay, it is the if the integral the mutual information, it is the I. If x and y as two variables or vectors, it should be greater than or equal to 0. There is a lot of things. Okay, and the minimum is 0 and maximum is there is no upper limit. Okay. Now I'm going to discuss some of the feature selection techniques. Okay. So here you can see this is a very well-known and very old that means mutual information based feature selection method. One is MRMR, that means minimum redundancy and the maximum relevance. So you can see in the equations, you can see the left part denotes the I means here mutual information between the two things. A5 means the features, the first selected features, or maybe the all selected features, I will be changeable, and C is the class levels. So here you can get, the thing is that every features suppose we are taking every features randomly, then try to find out whether the mutual information between that features, we already have the result, we already have the intensity values, that is called expression value here. Using that expression value or vectors, we can find out the mutual information between the that every features and the class. What is class here? Class means suppose we have the 100 samples are there. Maybe if you have 60 cancer patients and 40 non-cancer patients or normal patients, then we have a vector of that means 100. So here the size of the C is also 100. Okay. So we can make it Boolean, maybe 1 and 0 here. And if the cancer is there, we can write 1, and if it is non-cancer, you can write is 0. And for the original data, for the A, for gene, any data, actually this is the real-time data. Then the thing is that we have to normalize first. Normalize means we have to make scale gene-wise to make a, that means we have to make all the values in a particular range. That means maybe the 0 to 1 or minus 1 to 1. And then we can, that is, convert it into the Boolean form 0, 1 or 0, 1, 2, and then try to, when both the things in the same form, Boolean form, then we can apply. So left side is the called the relevance, right? So relevance, I said the relevance should be high, right? If any features has a higher relevance with that class level, the class vector, that means it provides the best, that is best uh, than the other features. Okay, and that means it can best define the class levels. That is the things. And the right side, you can say the I between the fi and fs. Fs means which is already selected, right? But that means if we when you choose the first features, then the right side will be 0 because either S means already selected. When you try to find out the first features, top features, then obviously in the destination that means side or selected side, there will be no, that will happen. So the right side for finding the first features, the right side will be 0. That means there will be no redundancy. When we find out, when we already find out the first top feature, then we try to find out the next features, then this right side will be active. And you can see there is a parameter tuning option is there. You can vary the weights depending upon different factors. Here they are using the S or something. S is the size of the set S that is already selected features. And you can see there is a lot of updated version will be there for this mutual information and feature selection where they are trying to update this weight factor. Okay. You can see another the version is the input normalized mutual information feature selections. Here you can try to change the that means weight variations. Okay, but the left side will be the same. So this is the feature selections. Okay, there is a lot of things are there. I am not going to the details. And at the latest, that means feature selection, which is very good, performing very well. It is called the variable weighted maximum relevance and minimum relevancy, and it is developed by one of my friends. Okay, and you can see it performs very well rather than the other methods. Okay, we already have some papers. We already sold this. So what is the evaluation criteria? So there is a lot of evaluation criteria you can use. One of my paper I have used the classification accuracy, redundancy rate, and representation entropy is there. So what is the redundancy rate? It is said that means for features, if having the d number of features, the redundancy rate will be the similarity between the two features. Okay, and there should be the that means deviations. Okay, and what is the representation entropy? It is defined here. This is one type, another type of entropy, and you have to understand that this representation entropy attains the maximum minimum value, that is 0, when all the eigenvectors except the one are 0. And when all the eigenvalues are equal, then it got the that means maximum value. Okay. So this is one of my that means very interesting work, and with my colleagues. That is the very computational work but here the thing is very big. That's why I'm not describing here. If you want interested, you can see this. First paper is the identification of multi-view gene modules using the mutual information based hypo graph mining. So here the graph mining method is used, and what we did that we make that is clustering using this mutual information and feature selection, and obviously some statistical feature selection already included. And this paper is published in the very good journal. It's in cybernetics. It was previously, and this paper is very good. And another paper which we made, here it is the multi-omics data. So maybe the omics means the genomics, proteomics. So all kind of omics, which ends with the omics, that is called multi-omics. That means sometimes it's there. Nowadays, only single omics data may not be make sense. Suppose if you go to any cancer that is hospital, you can get lot of data, lot of kind of data, gene expression, methylation, mutation data, because the COVID is coming. In the COVID, there is a 3OX is there, 3OX is there. So obviously there will be some mutation. So mutation data will also be available. So thing is that every kind of data has some dependency on each other. So our challenge with the computer science has a challenge how to integrate the multi-omics data or multi-modal data or heterogeneous data, considering not only the computational perspective, also the biological perspective. We have to consider and try to integrate. These are very good problems. Okay. So in this here, we try to find out the epigenetic biomarker. What is epigenetics? I already said there is a 3 levels: DNA, RNA, and protein. And when we work on the genes, so gene expression, that is in the RNA level. Okay. And when we go to the epigenetic level, that is the...
Sir, you are not audible. Dr. Malik?
I can hear you.
But your voice is not audible.
Can you hear me?
You can see your slides, etc.
Hello, can you hear me?
I'm not able to hear you. I mean, it's very, very low. The audio is quite low. Is it possible for you to log out and again log in?
Yeah, I'm trying. Can you hear me now?
Yes,
Hello.
sir, you are audible. Yes, sir, you are audible now.
Yeah. Thank you. So I'm starting from this that means slide.
Yes, sir.
It is
Sure.
okay. So I'm talking about the epigenetics. So here the epigenetics biomarker means any biomarker that will work from the DNA level. That means that biomarkers or features. Biomarker means features, set of features that is more stable, right? That is more stable. So this work is done by that means integration of multi-omics data. That means which has a gene expression and methylation. That means both the things are there. So this type of epigenetic biomarker is very useful, and that is more efficient than the only genetic biomarker. So this is published in the Nano Bioscience. It is also the computational work, and the latest within last months, one work has been that means accepted in the TCBB. It is the integrated strategy of the high-level clustering of the singular value decomposition and integrative biomarker discovery method with the application of the acute myeloid leukemia. It is one type of cancer, and we applied. We only tested our computational method. That means it is the unsupervised method on this acute myeloid leukemia. Okay, and it is also very interesting one. And now I'm going to some parts of that is network analysis that I already told that there is a motive finding will be there. So I'm just providing, this is one of my work. Okay, and it was published in cell level molecular therapy nucleic acid paper. It's the 8+ India factor. So thing is that I'm not going to the details because there is a lot of biological things, but I'm just providing the framework how we can able to connect with the computer science and biology to find out the motives. That means codons, you can say maybe. So because the background is that the link RNA will be there. Link RNA we already said that have a recently found to be important in gene regulation, and link RNA, one of the very well-known link RNA is H90, and here we are considering only H90 and here and the other things, not the other link RNA, only H90. So the thing is that link RNA H90 has reported to play oncogenic role. Oncogenic means which can make the cancer. Okay, in many human cancers. Okay, its specific regulatory role is still unknown. Okay, so here what we did here, we developed a novel analytic approach by integrating the synergistic regulation among the link RNA. Here it is H90 transcription factor. Transcription factor, you can see it is the one type of protein. Okay, which can impact the microRNA as well as genes, and any genes may be also transcription factors. So there is no particular definition of the
transcription factors, and there is also target genes and microRNAs. So you can say the multi-molecular network analysis, you can say. And how can we get that means data? We find out there is a lot of biological data reported will be there. One of the well-known data reported is PCG, another is ICGC, NCBI, there is a lot of. So what we get that identification of H19 TF gene triplets mediated by this microRNA. So this is the framework. I'm not going to the details. Here we are taking the 24 type of pan cancer, try to find out, we already have the H19. So we can get the expression. There is a two kind of expression, the lowly expressed and highly expressed. Okay. So we take the, that means 25 very low, that means lowly expressed samples, stop. And then according to that H19, we try to find out, we get the, that means the possible class levels and try to, and using this class level to try to find out which is the other related TFs and genes, because I already said that TF can target the genes and TFs. Sorry, H19 can target the TF and genes. Okay, and microRNAs also. So when we get the lowly expressed H19 lowly expressed samples, for those samples we try to find out the TFs, genes, okay, and the H19s. And similarly for the highly expressed samples, we try to find out the same things. And for the middle samples, we're just neglecting. Okay, and then try to find out the linear regression. And I already said the multi-omics data is independent, not independent, is dependent on each other. So here we are trying to find, that means eliminate the biasness of the, that means biasness which is created by the CNV, copy number variations, okay, from the expressions. And then we also make another regression. There is a lot of group-wise effect is there, transcription factors also there, and to eliminate that biasness from the data, we already make the another regression level, okay, and then we try to find out the triplets, okay. So you can, in the case tree, in the blue C, you can see there is a two scenario. First is H19 lowly expressed. You can see H19, the arrow is down, that means it is lowly expressed for some samples. For those samples, for the same samples, here you can see that microRNA is upregulated. There is a particular, some microRNAs are upregulated. Similarly, you can see that those TFs or genes which is targeted by those microRNAs are downregulated. So there is a one down, another is up, another is down. So these things is happening. Okay, so this makes a very good sense. Okay. And so this is the things, and there is a lot of experimental validation will be there. I'm not going to that details. This is the main things. Okay, and data collection, I already said that there is a lot of things are there. And how can you get the transcription factors? There is a lot of database trust. You can get that is transcription factors and gene interactions from this. Okay, and from the H19 targeted microRNAs, you can here we have found from the published literatures. Okay. And the main things in the pan cancer, in the TCGA pan cancer, we have considered 24 cancer types, not only one. That's why it is very important. It's the BRCA means breast cancer, and there is a lot of cancers, 24 types. So it's very important. And this is the regression. I'm not going to the details. Okay. And there is a triplet is finding, and triplets means the what I said that H19 microRNA genes or TFs. Okay. So result is like this, and here you can see the log p value is there and upregulation is there. Upregulation, downregulation means what I said. It can be determined by the statistical hypothesis test. Sometimes it is the parametric, sometimes it's the non-parametric test. So one of the parametric tests which is normally used by t-test, and for this particular, actually t-test is very old, and the thing is that it only works for the, that means if the sample size is higher and if it is the normal distributions, then it can work. But when you don't know the distributions, then I think the t-test is sometimes does not work or provide the wrong p-value, right? P-value is the probability value, and p-value is if it is the points less than 0.05, then it will be significance. That means actually p-value you can say that means if it is low, then it is good. That means it provides the randomness, right? If the p-value is lower, that means randomness is lower. That means very good. Okay. And another thing is fold change. Fold change is the that means the average value of the expression of the cancer divided by the average value of the expression of the normal patients. That means it provides how much the that is cancer level samples intensity will be higher than the that means the control samples. That means it is the factors or ratios. And if it is higher than the particular value, then it is called the upregulated. The upregulated means suppose we know the heartbeats. If the heartbeat is going very that is fluctuating very frequently and going very high, and if it is significantly high, then it is called upregulated. And if the heartbeat is going down significantly, then it is called the downregulated. That is the term. Okay. So this is the lab test validation for that result. I am not going through the details. Okay. So this is the one work, and now I'm going to the computation things that is very important for this. Recently, we have a one paper accepted that is in the ICIBM. What is that? The comparison between the 4 supervised feature selection algorithms leading to the top features and the gene signature from the multi-omics set. It is very simple, very straightforward. I am considering this work because it will be very helpful for the newcomers. So this is the flowchart. Suppose we have the omics data. Omics data means here we are considering each omic data individually. Okay, and you know any data should be normalized here. So here for the biological data, we have to normalize by the gene wise, row wise, feature wise. Not all the that is content of the matrix we can normalize at a time. It will be wrong here for this case. So here we have used the genomic. You can use any other. There is a hypermetric. There is a lot of other normalization technique is there, or standardization will be there. You can use this to scale all the vectors for each features. Then we try to find out what the statistically significant genes, that means statistically significant features. Okay, that means that by hypothesis testing. Here we are using the lemma. Lemma is very useful for the RNA-seq data. RNA-seq, one type of data. There is a lot different kinds of data is there, like microRNA, RNA-seq.
Sir, you are not audible.
Sorry.
Hello.
Can you hear me now?
Your voice is very low, actually.
Hello, can you hear me now?
Yes, sir, you are audible now.
I don't know. There is maybe the Wi-Fi problem is there. Maybe.
Yes, sir, it's okay, sir.
Sorry for the interruptions. There is a 1 minute. So I'm starting from this slide where I end. So then we try to find out that means statistically significant genes. That is using the lemma. Lemma is the parametric test here. But the thing is that it is very robust. It can be used to any kind of distribution, data distribution. That may be the normal distribution or any kind of distribution, non-normal distribution. That's why we are using here the lemma. Here the empirical based method is used. So if you want, there is a lot of other tools. You can use this. So you can see. So here we are trying to find out the statistically significant genes, and then we try to find out the top features among the statistically significant genes, right? So the thing is that why we did this, that means parallelly, because if we don't use the statistically significant that means genes, then it will be the biologically irrelevant, right? So because we need the upregulated, downregulated, and p-value significant genes, so obviously we need to use any statistical methods to find out the biomarkers or any biologically relevant features. So then we try to find out the top features using the different supervised feature selection technique. Here the MRMR. It is the comparative study. I am providing by which the newcomers will understand. And then we try to find out the classification performance. Here we have used the 10 times cross validations. Maybe here we have used the 10 times repetition. You can also add more. And there is a lot of 4 classifier has been used, C45, NAP based, KNN, and AdaBoost. And there are different performance evaluation metrics will be there. Accuracy, average classification accuracy, redundancy rate, representation entropy. Okay, and then we try to find out the biomarkers. Okay, parallelly, that means, and also what is the common one. Also, we already find out. So this is the basic things. Is the very there is normal things. So I already said the main thing is that in this multi-omics data, 5 individual omics of data is there, like gene expression, which works on the RNA side. Then exon expression, it is also in the RNA side. Copy number variation, it is also the RNA side. Then DNA methylation, it is the DNA level. And then pathway activity data set. And the tissue is there, the leukemia. Okay. And here you can see the class level is given. Maybe the 31 is favorable and the 96 are intermediate and 4 is 34. Okay. And 161 common samples is there. So you have to understand, as it is the multi-omics data, obviously we have to work on the common samples. When we try to integrate or any analysis from the multi-omics data, we have to take only the common samples. Okay, that includes all the misused data. Okay. I'm not going to the details here. This is the result. How can we represent how each feature selection method will be used and how their classification values work. And the VWMRMR works very good here. That's why I'm saying, because it works, that is very good in maximum cases. Okay, I'm not going to the details, and this is the summary data set. You can see there is we make some win-loss draw comparative study. Here you can see we just compare the performance. That means how much accuracy is good, better than the other. So the accuracy of the VWMRMR, how many times it will be better than the others. That is represented by WBL. Here you can see the first one 301, the first row and first column. You can see that cell. That means VWMRMR works. That means 3 times wins than the MRMR and 1 time loss. So this is the things. I'm not going to the details, and this is the overlap. We are taking now we have to find out the biomarkers. So what we need, we have to find out that means how much commons that or the common intersected that means genes are there among all the 50 that means top features. And here you can see the first for gene expression it is 7, and for exon expression it is 9. So it is one type of biomarker discovery. I'm not here. That means biological weight lab things is not given. It is the only one analysis done by my students. So I'm just try to say how this is the framework. Okay. So now the best things what I want to say now, the emerging topic is the analyzing on the single cell sequencing data. So thing is that I already told you the data format in the biological data omics data is provided by matrix, where the row denotes the features and column denotes the patients or samples. Okay, it is the normal case. But single cell sequencing data, it is a one kind of special data. It is also sequencing data where instead of the patients, individual patients, it works on the cell level. That means in the data, in the column side, instead of the patients, we can get lot of cells that may include that means one single patients or the multiple patients. Normally it is of the multiple patients. So thing is that we can't determine which is the cancer, non-cancer. We can't know the class level. So one problem is to find out the cell clusters. This is one computational problem of the single cell, not the other. For the other, it is given. Okay. And second thing is that when we see this single cell, why it is very important? Because in normal cases, in the biological data, number of patients or number of columns is very limited. Sometimes we got 100. Actually, it is depending on the hospitals. If the hospitals 100 patients data is collected, you will get the 100 patients data. But in the single cells, what will happen? It works on the cells. So here there is options to work on the multiple cells of the same patients. So obviously the number of columns, so it is more larger. It may be the 5,000, 6,000. Okay. And previously it works on that is in the normal sequencing data, it was only 100 or maybe the 200. Here it is maybe the 5,000. So here the option is very good, and it very works. If any model works in the single cell data, that means it is very good in the computational perspective, because the number of samples, you can say the scales is higher. Okay, that means population is higher. This is one thing. Another thing is that the main problem is that here there is a sparse matrix is zero. Sparse matrix, why? There is a, as it is works on the zero level, and that means cell level, so it is happen that lot of drops out will be get. That means zero values will be get, right? So lot of zero values you can get. So among these zero values, some of them are original zero values. That means original value intensity value is zero, and some of them are dropout. That means done by mistake. So there is a lot of ways by which we can tackle this. Okay. Sometimes in previous cases, what they did, they just neglect these zero things, which is dropout, which is not. They try to find out the highly variable that is features by using sometimes the PCA or TSNE. There is a lot of methods. Okay, but nowadays we started working on the imputing. We try to find out the imputed matrix. There are different methods like hashing technique is there. Using this, we try to find out the imputed matrix, and then on the imputed, using the imputed matrix instead of the original matrix, we try to find out the rest of the analysis like feature selection or classification. This is given. Okay. So here you can see that where it is applied, the study of the heterogeneous system. Here the different cell differentiation. That means I already said that sometimes the class level is here. The class level is not given for the cells, so it is big challenge to find out the cell differentiation. Okay. And another thing is the tumor heterogeneity, cell type identifications. That means also interference of the gene regulatory network across the cells. Okay. So what is the challenge? I already said there is a lot of noise, and what is 0 and 1, all the, there is a lot of dropout will be there, and sparsity will be there. So it is a big challenge to work on the sparse matrix. Okay. And this is the framework. You can see, read the QC quality control, then read the mapping, then quantification, then sales of QC means quality control, then normalization, then clustering, then differential expression. Differential expression means to find out the statistically significant genes, and here it should be the cell-wise, cell type-wise, right? And then the other annotation part, maybe the pathway analysis or gene ontology study. This is the things. And here also the same framework. You can see data exploration or quality control, then the normalization, and sometimes batch effect will be there. It's very useful. Why? What is the batch effect? Suppose any data is prepared in a lab, but it is not, the reading is not taking that is in one day. There is a lot of maybe it takes 1 month or more. So, and every time is the different person will be taking the reading maybe. So due to these things and the temperature problem, the batch effect will be happening. So there is a lot of methods, surrogate variable method, SVA method is there to correct this batch effect removal, which is called. And sometimes it is used, sometimes it is not. It depends upon that. And then we try to find out the feature selections. Okay. Then dimension reduction problems. I already said. Sometimes it is the PCA or TSNE used, and then the clustering technique, and then differential expression and enrichment analysis, and then the wet lab study if you want to do. Okay. This is the main problems. What I said, the sparse matrix and dropout finding. Then optimal cell cluster identification, disease specific biomarker identification, then reduction of the time complexity of the searching. And here the hashing is there. Sometimes
used, and then optimal classification of regression model finding. This is the main things, and there are a lot of other problems also there. Okay, this is one data repository. It is called the NCBI Gene Omnibus, and here the thing is that here the GSC number is there. By this ID, and even there is a name, you can easily get the data. So it is very user friendly. There is a lot of other site is there for finding the RNA set data or any single cell data, but it is very useful. Okay. And the main things, what I said, the clustering of single cell sequencing, that is the one part, cell clustering. So this is the one that is closure of the clustering method. What I said, the quality control. Sometimes gap statistics is used, and then data transformations, then feature selections. This is mainly used. You can see the PCA, TSNE, and there is a lot of things. Sometimes imputed matrix will be there, okay, before feature selections. And then for clustering, steward, that means method is very useful, normally very useful. And a lot of other greedy methods are also there. And this is the clustering portions. And here is a one type of gene selection method. I'm not going to the details. This is one type. Okay. This is a binary idea binary. And another thing is the graph clustering things. Here the graph clustering is that the gene modules, what I already described. Okay, where you can find the gene modules for the multi-omics data. This is one challenge. What we did in the cybernetics paper, there is a multi-omics data is there. By handling the dependency, we find out the that means heterogeneous gene modules. That is very important. Okay, and here there is a lot of other things are there, and I'm not going to the details here. And this is the, you can see this is the dendrogram, which can provide the relationship between the nearest relationship between the that means different blood cells. And here you can see the PBMC data. What is the PBMC data? This is one type of blood data, and for the single cell data, PBMC data is very useful, and it is a very standalone scan data, very that means well-known data. Okay, and sometimes this is the clustering of the cell types like this. Okay, and another thing is that sometimes one very good problem is rare cell identification. We know the outliers. So here the same thing applies here. When you make the cluster, sometimes we got some outliers. And you know the PCA or TSNE sometimes they cannot find out the outliers. So this outliers is called the rare cell type. Sometimes you can use the DB scan or something, density-based clustering, which can find out the outliers. You can also use, but you have to understand the other scenarios also. Okay, and in the accuracy measures, there is a lot of clustering coefficient will be there, like cluster accuracy, then salute width. There is a lot of as a clustering coefficient, a lot of cluster variety index will be there. And it can, I'm not going to the details here. This is the heat map. It is called the heat maps. You can see that means there is a dendrogram is there. Here the red color means highly, that means upregulated. That means the heartbeat is going high, and the blue means heartbeat is going down. Okay, so it is very interesting. If you can see here, this data, you can see the feature selection. It is the selected features. That means this histogram is made from the selected features, not all the features. That's why it looks very good. If we make a heat map for all the initial data, that means all the data without using any feature selection, you can make some hazy things, right? You can't get these clear things. Okay, so as it is done by the feature selection method, and we already make the heat map using this feature, that we selected feature, that's why it looks good. So these are things, and I'm not going to the details here. One thing is modularity optimization. This is the one part. Okay. And another thing is what I said, the locality sensitive imputation. This is one type of imputation by which we can generate, that means, or corrected the original data matrix for the single cell data, which can helpful to, that means, remove from the noise. Okay. This is the concept of the dropout events. Okay. And there are a lot of existing methods like DRI impute, SCL impute. SCL impute is very well known and very useful. And KNN in view. There is a lot of integration method will be there. I'm not going to the details. And why? And the main thing is that in the conclusion of what I said, what is the main things in now? The first thing is the multi-omics data. Multi-omics single cell data. Previously, I described the single cell data. Okay. Here the multi-omics single cell data, that is heterogeneous, or you can say in the population of this multi-omics data integration. How to integrate and find out the set of features. That means the signatures. And
so there is some problem from audio.
hello.
You're not audible.
Hello. Hello.
Yes, sir.
Yes,
sir.
yes. Now it is audible. Now it is audible.
I'm very sorry. I don't know what is happening because it is 1:30 here in night. That's why maybe the problem. I don't know.
Okay, it's fine. It's fine. It may happen as we are doing it in an online mode. So technical glitches may be there.
Yeah, because in my area there is a lot of other people are there. Maybe I don't know if they are working. Maybe it is disturbed.
Okay. You please continue. No issues. Please continue.
So the thing is that the second thing is the integration of the feature selection methods, maybe the supervised or unsupervised, and we have to integrate with the multimodal deep learning models. Okay. And the thing is that another thing is that multi-object, we can also use the multi-object optimization here. Maybe the parent optimal finding, maybe there is a lot of methods are there. And also another thing is that potential drug discovery. We know that there are a lot of drugs are available and they are discovered. And how to discover this? There is a data which is that is interaction data set, which is between the cell line and the drugs, and sometimes genes are there. So by this data, we can make some regression or classification model. We can add also some feature selection methods to find out which is the potential drug or drug targets. And also there is another thing is that which is called the prognosis study. Sometime in the cancer, what will happen? In the cancer, there is a lot of stages, stage 1, stage 2, 3, 4. And you know the stage 3 and 4 is very critical. If it is stage in 1, then it is, I think, curable. So if you go to the different hospitals, then one thing is there, they are counted from the first day of the reporting and until the date. If it is the diet person, it is called overall survival time. Okay, and if it is alive, then obviously the reporting time, latest reporting time. This day is calculated. Using this date, we can make some regression model and get some multivariate. We can use some multivariate Cox regression model and get some p-value, and we can find out whether it will get impact on that means prognosis level or not. Okay, this is also important. Okay, so this is all for today, and this is the references, and this is some of my collaborators in the USA. I just mentioned some of them because I have a lot of collaborators in the USA. I also work with the Ajay Goel. He's a very well-known person in the Junichi Yada. I'm still working with him. And Dr. Stephen Chen is a biostatistician, and also his wife, Lily Wang. And India, I also already worked with Sanvitra Bandhavadhyay, my supervisor, and Ujjwal Malik, my supervisor, and also Anirban Mukhopadhyay. And also I worked with Sohit Jamil, who's a very well-known person. I think many of you know. And in the China, I have a lot of collaborators also. I mentioned some of them who are the associate and assistant professors. And this is my contact information. If anybody want to collaborate with me, I have a lot of fundings, collaborations. So there is no problem. You can contact with me. And I have also a website. This is my personal website. You can get a lot of lists there. And also you can find my Google citation page. There is all the works are there. And this is my good memory. That means in USA maybe. It is not like that all the time we are working. We are also happy to make some, that means good time, picnic or something. It's a good memory. And thank you so much. If you have any questions, just tell me.
Thank you, Dr. Malik, for this excellent presentation on new insights to the domain of bioinformatics. So I would now request audience members to pose their question for Dr. Malik here. I think we had a raised hand from Dr. Shibun Parita. Dr. Shibun, are you there?
Yes, am I audible?
Yes, sir.
Yeah, yeah, audible. Please tell me what's your question.
Uh, Very good. It was a nice presentation.
Thank you
My
so
name
much.
is Sibun Porida. I'm a faculty here in the UAM. So, sir, I have few questions. It's
Yes.
better I will ask one by one so that it will be easy for both of us to explain. So,
Okay.
you have mentioned initially about the mutual informations and
Methylation.
mutual information.
Mutual information. Okay. Yeah.
Yes. So I'm starting with the mutual information. So the mutual information, when you explain, that means you're calculating, identifying the association. Means there is some relations, linear or
Shared
relationship
knowledge.
is there.
Shared. Non-linear. Here it is a non-linear. If you
Okay.
use any correlation, that only counts the linear relationship. But if you use the mutual information, it can count the non-linear relationship.
Okay. Now, okay, my one is over. Second one, you have mentioned about the multi-omics data, and in
Yeah.
multi-omics data, you have mentioned that it is dependent on each other. The features are,
Yes.
the issues are
Yes.
dependent on each other, and that is the reason you have mentioned about the linear and logistic regression over there, if I'm correct.
Yes.
But what I found in your workflow, you have mentioned also that supervised learning method like SVM and something like that. And where we understood that in SVM, and when we are creating a model, that features must be linearly independent to each other.
Yes.
So
Yes.
how it is an ensemble method means one hand you are saying that it is linearly dependent the feature set, and one hand you are using the SVM.
I understand your point, but you have to understand, if you go to the heterogeneous data, then you have to understand, suppose I am saying the DNA methylations. DNA methylation is just adding it does not change the sequence level, it just adds in the sixth position or third position of the carbon, the CH3 group or methyl group, and it can just means going down the expression. So the relationship between the DNA expression, DNA methylation and gene expression is inverse. And if you see the copy number, if the number of copy number is increasing, then the gene expression also increasing. So you can find lot of factors, which sometimes it is increasing, sometimes it is decreasing. So I understand your point, but the thing is that we can't, that is, do in one factors. Okay, so we try to find out when we add this information, the dependency, then sometimes we use that means multi-objective approaches to find out the best possible solutions, because obviously what we do sometimes it is correct and sometimes it is nearly correct. We can't say it is the 100% correct. Suppose we discovered anything, maybe in future, maybe somebody says that there is a problem. It may be problem, maybe. The thing is that any problem here, the multi-omics data, I'm saying about the multi-omics data. Multi-omics data, that means what you mentioned, that means when you integrate this, then that is a big challenge. And this integration you can do by the multi-object optimization or any other things. So by seeing the one factor, I can't say anything. Okay, that is my answer.
Okay. So my third question is, you have mentioned about the cRNA network. Coming to the network analysis, you have mentioned about motif network. You have mentioned about the microRNA, long non-coding RNA interaction network analysis. Okay, that's cRNA network analysis. So my question is over here, you have mentioned, you have identified the target mechanism. You have mentioned few tools, but what I have found, those tools are specifically designed for microRNA target identification, that is miRNA, mRNA interactions. So how this long RNA, miRNA interaction, how do you think the specificity is still hold?
I got your point. If you see my slide, I already mentioned the interaction between the long non-coding RNA and microRNA. It is found from the literatures, and we found maybe the 60 or 100 literatures we just collected, because sometimes it is happening. If you want to find out, as you said, the target detection between the microRNA and the genes, you can get lot of. And if you want to find out the relationship between the interaction between the TF and microRNA or TF or genes, there is a transpact or trust. There is a lot of. The thing is that this H19 or long non-coding microRNA, it is very new, and it may be. I'm sure that lot of researchers are working on to make the database between the interaction between this link RNA and others. But here it is the very latest, and 2 years back, one of my friends this collected, they have not found any database to get these interactions. Okay. He studied 60 or 100 literatures and then he found out these interactions. According to the, obviously this is the good journal, not the random journals. The good journals, from the good journals, they are found.
So you also consider the literature mining or text mining as along with that identify your finding.
There is no other option. There is no options. We already that means selected those literatures which has a wet lab validation.
But sir, can we have also seen that people have seen long non-coding RNA, mRNA identification target prediction, and microRNA, mRNA target prediction, and they are trying to see that network analysis from there. Can it be done over there?
You can do, but when you make the network analysis, there is a lot of options.
Dr. Manik, your voice is breaking. I think there is some problem.
Hello?
Yes, you are audible partial. Hello.
Can you hear me?
Yes. Okay. Now, my next question is that you have mentioned about the common samples. So that common samples related to the common gene set.
Common genes, sometimes you does not get a common gene. Because if you have the microRNA data, if you have the mRNA data, that means mRNA is gene
Your voice,
data.
sir, your voice is breaking.
It's not audible.
Okay. Hello.
Yes. Sir.
Yes. So can you pardon the questions?
You have mentioned about the common samples. Once you identified, you have mentioned about the common samples, and that those common samples are you referring to the common gene set?
No, that's I'm saying that for the multiomics data, if you have 4-5 data, multiomics data, so one data may be the gene expression data. That means the feature is here the genes.
Yes.
If you see the DNA methylation data, then the features will be the probes, and you can probe. You can that means get the interaction between the probes. That means you can make the link with the probes and the genes very easily. There is a lot of database over there.
Yes.
So you can get the information, these two information from the genes. That means at least the genes. If you see the microRNA, then what can I say? The microRNA is different. You can't say the common.
No, you will not get that.
So here the only options you have to work on that means columns. That means you must be work on the same kind of patients. If you see the TCG or ICG, suppose you are checking the DNA methylation, you can get maybe 200 samples, right? And for the if you see for the same tissue or for the same data sets, if you see the that means gene expression data, you get maybe 150 data, 150 samples, right?
Agree.
So if you want to do, there is an ID number is there. You have to match with that ID number, common ID number.
Yes, gene ID, yes.
You have to match with that, and you have to obviously work on the common samples. That means common IDs. Otherwise, it will be wrong, totally wrong thing. So you have to understand this. Everything you can do, but you have to take the common samples from the beginning.
Okay. So, sir, my next question coming to the single cell part of the things. In single cell, what I understood, I'm just learning the single cell. Once you identify the clusters, how will you annotate? Because suppose I have three cluster groups that I have identified. Now, how will I annotate those gene set to a different pathway or functional name? Because I don't know. So, do I need to map that?
For the path analysis, there is a lot of that means gene set enrichment.
Yes, that I know. But in Surat, how you do that GACI analysis?
What I got, one of my students is working on the Surat. They have provided that means framework, but there is I found there is a lot of that means issues are there.
Yes.
Obviously, when the Surat has been that means it is the first well-known tool for the single cell. That's why it is that's why it is highly cited. But you can see there is nothing is about the imputation. What I described, the matrix imputation will be there. You can't get any imputation in the Surat lab, right?
Yes.
That means when the imputation things comes, then Sirat Lab has not discovered. So it is the initial things. So I suggest there is a lot of methods. I can maybe mail you. There is one of my colleagues, which is Debarko Sengupta. He was the assistant professor in the IIIT Delhi. I can also mail you. You can mail me. I can send you the papers. He makes some imputations. I think that that means that things are very good, very good. Rather than it works better than that Mr. Lab. I think he has already make some comparative study. So,
Okay.
so I think
Okay,
you can check this paper. I think it will be very useful, and the code is given. Code is given in the, that means GitHub. That means they are using maybe the ArtScript code. Okay, I think.
Okay, sir. Other participants are there for asking you question.
Yeah,
I will not take much of your time. If I have,
okay.
I definitely
If
write you
you
over
have
the
questions,
mail.
you can mail me. Okay.
Yes, I definitely write you a mail.
Okay.
Thank you so much.
Thank you, Dr. Malik, for answering these questions.
Yeah. Thank you so much.
Thank you, sir. We are grateful for the time and effort you took to share your thoughts. We have a small token of appreciation from the organizers of GCAIA. Please accept it with our sincere thanks.
Thank you. Thank you,
sir,
for the honor.
Thank you, sir, for joining us today.
Yeah. Okay. Stay good. Okay. This is the COVID time, so you have to be careful about the third wave. Okay. Thank you all.
Okay, sir. Take care.
Okay.
For the third research keynote speech of the day, I would like to invite Dr. Albert G. Nasipulin, professor at Skolkovo Institute of Science and Technology, and an adjunct professor at the Department of Chemistry and Material Science of Aalto University School of Chemical Engineering. A PhD in physical chemistry from Kemerovo State University, Professor Albert Nasipulin has specialized in the aerosol synthesis of nanomaterials, investigations of their growth mechanism, and their applications. He has a successful background in academic research with about 300 peer-reviewed scientific publications and 40 patents. He is also a co-founder of 3 companies: Canatu Limited, which is a spin-off from Helsinki University of Technology, Finland, and Cryptochemistry and Nova Print, which are spin-offs from Skolkovo Institute of Science and Technology, Moscow, Russia. I would now request Dr. Nasipulin to start his keynote speech on single-walled carbon nanotubes from the synthesis to applications. It's over to you, sir.
Thank you very much, Mrs. Chairman. Yeah, sorry. Yeah. For this nice introduction. It is nice to see you. Can you hear? Can you see the slides?
Yes, sir, we can hear. And we can also see the slides.
Very good. So let me start my presentation today with 2 simple questions. Here's the first one. Can anyone in the audience identify if you do not have a mobile phone? Yeah, I believe that nowadays everyone actually possesses mobile phone, a gadget like that. So the second question would be, who has a Nokia mobile phone? And I assume that nobody would positively answer my question, but can you imagine that only 14 years ago, magazine Forbes on cover questioned, so can anyone catch the cell phone king? So only 11 years ago, actually, Nokia was the most spread gadget in the world, and nobody could even imagine what's going to happen in the nearest future. So where is Nokia nowadays? Actually, I started this my presentation with 2 questions. So first, to show how rapidly our life changed from technological point of view. Like 20 years ago, practically no one has mobile phones. Now everyone possesses. So it's very difficult to find people without that. And also Nokia, being the first leading company during just like a few years, stopped completely. After a few years, so the Nokia lost its leading positions. So they had different mistakes, but one of those, so I would like to tell you today, is about they didn't put enough actually attention to develop transparent conductors in smartphones. So that's what we are going to touch today. So I'm from Skolkovo Institute of Science and Technology, and that's a new university which was established only 11 years ago. So this campus was built, and only like 3 years ago we moved in it. It is the first English-speaking graduate university. So in addition to education, we take care of our students so that they spend a lot of time during their studying at Skoltech to innovation, and also we growing them up to be entrepreneurs. So during these 10 years, according to Nature Index Young Universities in 2019, so we are ranked globally number 97. So today I'd like you to change a little bit topic from what you are doing, from machine learning stuff, artificial intelligence, to think about materials. And I'm representing carbon nanotubes. So this is amazing material, and I would like to tell you about this one. Of course, I will also touch machine learning techniques which we utilize to make our carbon nanotubes of the highest quality. So let me start with carbon nanotubes. Do I need to explain what it is? I think you all heard about it, especially after receiving a Nobel Prize in 2010. So you all know what is graphene. Graphene is a single layer of carbon, but if you make a cylinder out of it, you're going to get a single-walled carbon nanotube. So the beauty here is that whatever piece of graphene you're going to take, so you can get a carbon nanotube with different properties. For example, as an example, here you see a metallic carbon nanotube and semiconducting carbon nanotube. So basically, all the needs for electronics is covered. You could make conductive material, you could utilize as a conductor. At the same time, you could make field effect transistor out of semiconducting tubes. So I started to work on this topic almost 19 years ago, and still I continue, because this is the best material. I have to say it is a champion among other materials according to its properties. So this is the best conductor of electricity, best conductor of heat. So it is a very strong material. At the same time, you could utilize it as a semiconducting material and make field effect transistors better than silicon. Thermally stable, you can heat it up to 1500 centigrade. At the same time, it is very light and stronger than stainless steel. Depending, on the field of science and technology, you could always find, practically in any field, you can find a niche where the carbon nanotubes alone or as a composite might improve the performance of different devices. If you take like electronics, there are different applications, functional structural materials, medicine, energy, and one can continue. I'm not going to list this today. What I would like to show you just a few personal examples we have been working. So how to synthesize carbon nanotubes? There are a few different methods. According to carbon atomization, you can divide them into physical and chemical. Physical means you sublime the material, evaporate, and then you desublime in forms of carbon nanotubes. To evaporate carbon, graphite is not actually a very volatile compound, so you need a tremendous amount of energy, which could be applied using arc discharge, laser ablation, solar energy, induction heating. So this method were used in the beginning of carbon nanotube studies, like 25 maybe years ago, because they require very high temperature, very low control of input parameters and output parameters. But the chemical way, which is based on decomposition of carbon-containing compounds, which are hydrocarbon, CO, or alcohol, or whatever actually compound which contains carbon, could be utilized to grow carbon nanotubes. So this method does not require very high temperatures. So 1000 centigrade is enough to grow high quality tubes. In turn, this method could be divided into substrate supported CVD and aerosol. Substrate supported CVD, you take an inert substrate, make a catalyst on the surface, put it in the reactor, wait 20 minutes, and after 20 minutes you take it out and enjoy your growing stuff on the surface. So 20 minutes. The aerosol, some people call it floating catalyst method. So this method is completely different. You have very limited residence time. You need to control quite many parameters. So in our laboratory, we have developed like different methods. So the main difference is how you create a catalyst particle. Catalyst particle is a prerequisite for the synthesis of carbon nanotubes. You could evaporate, for example, you could evaporate metal directly by resistive heating from hot wire generator, or you could decompose metal containing precursors. So here is an example so that you got an idea, and then I will show you how we could apply machine learning to optimize this process. So this is ferrocene. It contains an atom of iron, which is the catalyst for the growth of carbon nanotubes. It is volatile at room temperature. So we fill cartridge with a ferrocene. Carbon monoxide, it is a carbon source, which gives us carbon. So carbon monoxide is a gas which goes through the ferrocene cartridge, saturates with a vapor, and then we introduce the vapor gas mixture into hot temperature reactor heated up to about 1000 centigrade. Ferrocene decomposes and creates catalyst particles, 2 to 5 nanometer, which catalyze disproportionation reaction. CO plus CO gives you atomic carbon, which is needed for the growth of carbon nanotubes. So the flow is going through the reactor. We have a very limited residence time, up to like 20 seconds maximum. And then the carbon nanotubes are collected downstream of the reactor by filtering. So there are so many processes which you need to worry about and to take care. First, precursor decomposition, then the catalyst particle formation, coagulation of catalyst particle, nucleation of nanotubes, carbon source decomposition, nanotube growth, and at some point you're going to get the termination of the carbon nanotube growth. And then there is a bundling, deposition, and so on. Basically, that's how the carbon nanotube grow. But when you grow them, you could enjoy their properties. Here is a filter, which was originally A4 size. With a scissor, we cut the size of the electrode we would like to give, and then just press it against the substrate where we would like to transfer. So you see that the carbon nanotubes, they stick pretty much well to practically any substrate because they have high specific surface area, but at the same time, they don't like the material from which a filter is made. You could transfer it to glass, to polymer. If you look at transmission electron microscope, you see that they contain some unused catalyst particles, and it is randomly oriented network of carbon nanotubes. The beauty of this method that you don't need to do anything. You just deposit them, and it's ready for many applications. So that's what I'm going to show you. So, of course, any material must be characterized from physical-chemical point of view. So the Raman shows actually very strong G band, which is responsible for graphitic carbon, practically absent D band. This is disordered carbon. And the ratio of this peak tells us about the quality. The higher G to D ratio of intensities, so then the better quality carbon nanotubes we have. So on the left side, you could see a radial breathing mode, which tells us about the diameter of carbon nanotubes. So if we look at optical UV visible near infrared measurements, we also see quite a lot and can learn a lot about our samples. Those samples were produced at different temperatures, and you see the features which are called S11, S22, and M11. This is so-called Van Hove singularities in quasi one-dimensional structures. So if you look at the electronic density of states of semiconducting tube, you see S11 transition is here, this is S22 transition, and also the gap in metallic carbon nanotube, which is larger. You can see all these features in the optical absorbance spectrum. So playing with the temperature, you see that you could change the absorbance, therefore covering practically the whole range from UV, ultraviolet to near infrared range, which is quite important for optical applications. But also you see that the diameter is changed of carbon nanotube quite significantly from 1.1 nanometer to 1.7 nanometer. So what could we do? How can we improve? How can we control? We all nowadays live, of course, in the world of computers. Computers not only help us to live, but also very often started to actually drive our life. We also wanted to teach our computer so that it could produce the carbon nanotubes of a quality of a certain property we would like to have. So the data set collection. So that's how we start. So the Raman spectrum, as I showed you, shows you intensity ratio, G to D peak. The larger the G to D, the higher quality we have. There's also the absorbance spectrum. It can give us at least two things. So first of all, yield. So the absorbance, the darker the film, the higher the yield, if you collect it over a certain period of time. And then from spectrum you could get, and also the diameter of carbon nanotubes is changing depending on the conditions. So you create your samples. So this is the output parameters. Now, how can we control and change those parameters? There are 5 input parameters. It is the pressure of CO. CO, if you remember, it is a main carbon source. Then CO2, which we found quite important for the synthesis, which allows us to change the diameter of carbon nanotube. Concentration of ferrocene, and then temperature inside the reactor and total flow rate. And then we applied an artificial neural network to find the correlation between input and output parameters. So it was 3 independent artificial neural networks with the 5 input parameters and 3 independent output parameters. So we start our data preparation with a transformation so that our model can take it. And then all experimental data we split into 80% for testing and 20% for training. Unfortunately, aerosol synthesis of carbon nanotubes, as many other experimental methods, is time and resource consuming method. We do not have a variety like thousands or many thousands experimental points. So the best what we could get by this period of time was 98 experimental points only. And that's already like almost a year of experimental studies. So of course, that's not enough number for any successful help from the artificial neural network. So that's why we applied augmentation data. Every point was multiplied by 20, so we got almost 2,000 points. And then after the normalization, so we come to the artificial neural network, playing with the parameters like number of layers, nodes, batch size, and so on. We were able to minimize our loss. Loss is a relative absolute error. And here you could see how our artificial neural network actually predicts the experimental data. This is the experimental error, which is 0.7%. while the prediction error was 4%, so which is actually not so bad, taking into account how scattered experimental data can be. Very similar situation we observed for the ratio G to D, where the after a certain period of epochs, we see overfitting problem. And so for yield, we could also predict is at least an order of magnitude is pretty much the same. Experimental error 5 and prediction error is 14. So here I also would like to pay an attention how important was to introduce augmentation. Without the augmentation, we have the errors like 10% for the diameter. With augmentation, it's only 4%. So for yield and for G to D ratio, so the error without augmentation was 2 times larger than so with augmentation. Now we produce nice tubes we could predict, and so what can we do with those films? So we were inspired actually with flexible, transparent, and elastic components for future electronics. So if you look at this series of gadgets, you see how they were evolving, changing with time. And if you look at this one, this is a prediction of different concepts of phones. But to expect that you can fold your mobile phone, you could roll it, so you really need the new kind of materials. That becomes even more important with appearance of new kind of electronics, variable electronics, when which allows you to monitor practically all the parameters of our body: heart rate, hydration rate, body temperature, like UV exposure, and things like that. So for that one, you also need to make this flexible, transparent, and elastic electrode. The method actually we are producing, aerosol CVD, synthesis of carbon nanotube, fulfill all the requirements for flexible and stretchable electronics, because we could fabricate the electrodes on a plastic substrate, which means at room temperature, because you cannot heat up plastic to high temperatures. And also it is price compatible with existing technology. You don't need vacuum. It is with very high speed and allows you to roll manufacturing. How about the existing technology? For example, silicon and transparent conducting oxide. For example, ITO, indium tin oxide, which is utilized in 75% of mobile phones as a transparent conductor for smartphones. So can we utilize this material for flexible and stretchable electronics? Yeah, unfortunately not. Here, I always show this a classical example by Professor Yang-Hee Lee. So when he showed that if you deposit ITO in a polymer and start to bend it, you could see that the sheet resistance started to increase. So it becomes less conductive. But when you put it in an initial position with a bending angle 0, you're never going to get initial sheet resistance, because practically you break the electrode. It is so fragile. How about carbon nanotubes? Whoa, with carbon nanotubes, you could survive, no problem. You could bend, you could, depending on the substrate, the increase in sheet resistance could be different, but it tolerates 150,000 cycles with a radius angle of 2 millimeters, while ITO or other transparent conductors will be actually broken. Well, since we're talking about transparent conductors, there are 2 parameters we have to take in our mind: is it transmittance and sheet resistance. We would like to reach ITO on rigid substrate. It is 90% transmittance and about 10 ohm per square. It's somewhere here. This is a picture from my publication from 2011, where we first beat ITO on a flexible substrate. So you see, this is a progress. So 2010, it's 108 ohm per square, 2015, 65. So we still need to improve to come down to 10 ohm per square. What can we do? What is the next stage to improve the conductivity? of our transparent conductor films. Again, if we carefully look what kind of parameters really affect the conductivity of our carbon nanotubes and their properties, we could distinguish at least two of them: is a CO2 concentration and also temperature. They have the most powerful effect on the synthesis of carbon nanotubes, considering all kind of processes which happens during actually the growth. You could think about like absorption, dissociation, desorption, carbon diffusion, growth, like many parameters which we do not have even a single model to predict how the carbon nanotube grow. But again, we have the help of machine learning. This is a very like a simple way how it could be utilized. So the whole step from synthesis, characterization, data set, training, prediction, and verification. So let me show what we did for that one. So we distinguished two of the most important processes. One is a CO concentration, the other one is temperature. And what we would like to optimize, since we are talking about transparent conductors, it is a sheet resistance of the film, which is 90% transmittant, okay? So this is like a universe property of the material, so of transparent conductor material. So at different conditions, we synthesize our films and measure sheet resistance. And that's what we are going to see. We characterize this material with the use of transmission electron microscope. So the blue one shows a very high sheet resistance, so not so conductive film. And we see that the carbon nanotubes exist, but they contain a lot of unused catalyst particles. For the films which are the most red, if I can say so, we see that the carbon nanotubes, they do not contain so many unused catalyst particles. It is a nice network of carbon nanotubes. So depending on the color, we could always identify the position, but can we identify where is the minimum? So at what experimental conditions we could produce the film which would have the lowest sheet resistance? How to do this? Yes, you could utilize the support vector regression, as that's what we did. And we found a maximum. It is like a prediction out of this data. We can find an extremum. So let's start from the beginning. So first we synthesize with the carbon nanotubes a batch of samples. So these samples go through the training with the support vector regression. And then we are going to get the surface from which we find a local minimum. This local minimum would tell us that this is the best conditions for transparent conductors. Then we go, and this data actually corresponds to this temperature, 854, with a concentration of CO2, 0.93. We go to reactor for the verification. We synthesize carbon nanotubes at these conditions. And then we get 39 ohm per square. So that period of time was like 2 years ago. It was a state of the art for transparent conductors. So you could apply the machine learning to improve, to optimize your certain properties for certain application, as we did for transparent conductors. So transparent conductors. Now we have this material. What can we do with this? Now I just would like to show you a few applications. So for example, we started to work with a touch sensor. This is a single pixel touch sensor. The carbon nanotubes are here. You cannot see them. They are transparent, but at the same time, they are conductive. Our collaborators, so they did OLEDs out of carbon nanotubes, where the ITO level was replaced with carbon nanotubes. And our startup company, Keynote, the name came from carbon nanotubes. It is located in Finland, and they started to work actually on improvement of transparent conductors for Nokia phones. And we actually made 80 mobile phones and showed how good could be transparent conductors made of carbon nanotubes. They could replace it. They were actually cheaper, and you could also make them flexible or stretchable, so if needed. But you know what happened that period of time? The Nokia company was purchased by Microsoft. Microsoft actually didn't want to improve those phones, and so they stopped the R&D project with Keynote, and Keynote is a company who is commercializing the approach, how we synthesize the carbon nanotubes. I explained you. So needed to find their own niche. So let me show just like advertisement movie about the company who is making transparent conductors and utilize it for many different applications, particularly for automobile industry. So if you look at the car panel, you see it. You practically can make every single point in the car active. You could make it as a knob, but not a convenient traditional one, which you could need to screw, but only by touching, because you could make touch sensor out of any substrate, any surface. It could be glass, laser, plastic, or whatever. You can also stretch, you can give any shape. So I'm glad also to tell you that there are already cars which could be found utilizing our carbon nanotubes as a transparent conductors. Okay, so what else you could do? For example, you could make a solar cell. So in a solar cell, so you utilize N-type silicon and put a P-type carbon nanotubes. There is a heterojunction, which we applied to collect electricity by irradiating this with the sun. So this is like a solar cell with a quite high efficiency for that period of time, was like 11%. This is polycrystalline silicon. In our laboratory, I was more interested in stretchable or in a flexible solar cell. That's why we started to use with amorphous silicon. Amorphous silicon can be actually flexible, and years of work on this topic with carbon nanotube. So you have amorphous silicon layer on top of which you have carbon nanotube. It's not simple just a carbon nanotubes. It's a very good composite which consists of conductive polymer P.PSS, anti-reflective coating PMMA, and also carbon nanotube fibers, which are made of the same film, as you could see here. They showed the efficiency of 8.8%, which you could compare, for example, with amorphous silicon solar cell finished with N-type or P-type amorphous silicon. Carbon nanotubes, they really make it better by 1.8%. So, and this is related because we were able to also improve the shift resistance of the film down to 17 ohm per square. Now we are very close from ITO on rigid substrate, 10 ohm per square. Beauty of this material is that you could make it also stretchable. So we deposited carbon nanotubes on polydimethyl siloxane PDMS elastomer, and then when you stretch it, so what you see that the intensity of light emitting diode is decreasing. Why? Because when you stretch, what actually happens? The resistance goes up under strain, and then the total current through the chain drops down. And that's why the intensity goes down. But there is another approach utilizing exactly the same material, which allows us to make a transparent conductor, which will not actually feel the strain. For example, here, we first pre-strain PDMS. So, and then we deposit carbon nanotubes, and then we release it. In that case, we are going to have these micro-sized wrinkles, which basically provides a stable situation when you strain the material. Resistance does not change. As you could see here, when you strain it more than 2 times, you cannot actually even expect that the material, sorry, You cannot even expect that the same material could be utilized for these two different applications. You strain it, and so it is changing the resistance, or vice versa. Under strain, it does not change the resistance. And the reason is because of these wrinkles, they actually provide constant resistance. So when you strain it, they become flat, but the distance between electrodes remains the same. And the structure does not actually change much. So where and how we could apply this material? It could be utilized actually to make the active and also passive components for electronics. By depositing them on a finger, you could see that you could actually detect even a small movement with your finger, because it can feel really the change in the resistance. From the other point of view, you could utilize for stretchable application. A good example would be if you take ECG device, remove a copper electrode and put carbon nanotubes with a gel. So in that case, you see that the noise level came down actually compared to the commercially available electrodes, because carbon nanotubes in this case do not feel change in the resistance in the strain. And so last application, so I wanted to, not application, but configuration of this material, I would like to show. We could make freestanding film over a quite wide range. And here you could see how we could make it. So if you take a substrate with an opening, so we take a polymer, make a hole, and press it against the carbon nanotube film. In this case, we are going to detach it from the film, and this is a freestanding film with a thickness of about 10 to 20 nanometers only. How you could utilize it? So here is a nice example. You could create the sound in the audible range. So it is so-called a thermoacoustic effect. When the sound is created not by movement of the membrane, but very quick heating and cooling down. Thermoacoustic generator based on single-walled carbon nanotubes. It is, of course, transparent, and at the same time, a very thin and flexible material. And if you compare it with other material, so we found that it generates also ultrasound at the level of state of the art when you compare it with different other materials, like with a sound pressure level over 100 decibel. So you could also generate ultrasound with such kind of membrane. And there are many other applications. I don't have time to go through all of them, just only list. Like you could make a very sensitive electrochemical sensor freestanding film. You could heat air by passing the air through the carbon nanotubes. You could heat the air more than 100 centigrade, which is important for sterilization of air. You could utilize it as a filter for aerosol particles that become even more important in the era we live now with the COVID stuff. And also for extreme UV lithography, we need to protect the mask. Our carbon nanotubes could be a quite wide actually range, and they are transparent for extreme UV for 13 nanometers. We could make as a bolometers and ultrasound, as I showed you now. So I hope I was convincing to prove you that the carbon nanotubes is an excellent material, and the method we are producing the films has great potential in the future. It is at low temperature, non-vacuum, simple, fast process, low cost, and especially utilizing the machine learning would allow us to significantly improve the properties of our material. So at the end, I would like to thank the foundation, and I would like to thank also my group for participating in this presentation. Thank you very much, and I'll be happy to answer your question.
Thank you, Dr. Nasibulin, for delivering a very interesting presentation. I would now request audience members to post their queries in this forum now. If the audience members have any queries, they can post these questions. Sir, I hope it would be okay if they post their queries to you via email later on. No?
Sorry?
I said if any questions are sent to you via email, would that be okay?
Yeah, that's absolutely fine. Yeah, thank you very much.
Okay.
Yeah.
Thank you, sir, for gracing us with your presence. We have a very small token of appreciation from us, from the organizers of Gcaia. Showman, sir, if you would please.
Definitely, ma'am, I'm sharing it.
So this is an award of appreciation for you.
Thank you very much. Yeah.
I'm sending it to you via mail.
Okay, thank you.
Most welcome.
Thank you. Bye.
Thank you, sir.
Bye.
Now, please join me in welcoming Professor Panayotis Sarigenitis, Associate Professor in Department of Electrical and Computer Engineering in the University of Western Macedonia, Kozani, Greece. A PhD in Computer Science from the Aristotle University of Thessaloniki, Greece, Dr. Panayotis has published over 200 papers in international journals, conferences, and book chapters, including IEEE Communication Survey and Tutorial, IEEE Transactions on Communication, IEEE Internet of Things, and so on. He has been involved in several national, European, and international projects. He is currently the project coordinator of 3 H2020 projects. He also serves as a principal investigator in the H2020 SUTS 2018, SDN Microsense, SDN Microgrid Resilient Electrical Energy System, and in 3 Erasmus plus KA2. His research interests include telecommunication networks, Internet of Things, and network security. He is an IEEE member and he participates in the editorial boards of several journals, including International Journal of Communication System and Eurosep Journal on Wireless Communication and Networking. Now I would request Dr. Panayotis to deliver a speech titled Next Generation Internet of Things, Requirements, Applications, and Paradigms. It's over to you, sir.
Thank you so much for your kind introduction. Thank you for the invitation. I'm sharing my screen now. I hope you can see my screen.
Yes, sir, the screen is visible.
Great, thank you, thank you. Thank you once again, thank you for the invitation. I'll be very glad to present you some research and project findings based on their work we're doing in the University of Western Macedonia in Greece regarding next generation Internet of Things. So I'm Panos Aragianidis and I'm director of Ithaca. That's a new lab, but very active, I can say, a very active lab consisting of more than 19 members, funding more than 3 million euros in about 3 years. 6 projects coordinated, between them 3 H2020 projects. You know, Horizon H2020 is the most, let's say, effective funding tool in European Union. So we're very happy to have over 50 collaborating partners, more than 14 projects in total. So we're very active, and most of our projects have to do with next generation IoT. So briefly, I would like to give you just a flavor of what we are doing in the Ithaca lab. For example, this project, Terminal Next Generation Smart Interconnected IoT, is our flagship since it's on the heart of next generation IoT with a total budget of 8 million euros and a very balanced and very interesting consortium here. Since large companies like Ericsson, SMEs, a lot of SMEs, universities, and research centers are trying to provide a next generation reference architecture here. So we'll try to open the market for new IoT devices and also to see how new technologies like SDN, edge computing, mobile edge computing, and NFV could help the current state of Internet of Things to evolve to next generation Internet of Things. More than that, we have also some cybersecurity IoT related projects like the Spear one, which is focused on energy domain. So we try to protect, all the IoT infrastructure behind the SCADA systems and all the energy related systems from the production to the distribution. Also the SD microsense, it's a very interesting project where we try to detect threats and attacks, but also to mitigate the cyber attacks. So we try to, bring together the network level coming from the IoT and the electricity, the electrical level coming from the infrastructure. Also a new project that begins now in October. And also I can say some things about Mars, where the smart farming, which is one of the major, let's say, applications of next generation IoT comes into place here. So we try to see how UAVs, the drones, GIS systems, cloud services play together in order to provide better services to the final user, to the producer here, and to the agronomists. So let's see how the IoT evolves to the next generation IoT. So coming from the human-to-human per-internet communications, we evolved to the internet of content. So main services like email, 3W, and very basic information services came into place here. Then we went through the internet of services, so Web 2 came into playground by providing something services. And then going smarter and smarter, we proceed to the internet of people with social media, all the services that exist on the top of all the critical infrastructure behind it, all the protocols and the devices and the network protocols. And now we evolve to the Internet of Things, where one of the major challenges has to do with the machine-to-machine communications, where terms like identification, tracking, metering, automation, cybersecurity, trust, and all these things gain more attention than before, since all these stages have covered more or less the main challenges regarding the technology, the main technologies and the support. So we need to enhance more on the edge computing, on the AI, the trust, and the cybersecurity and the protection of the services now. So here is a very indicative cycle starting from stage 1, where we have device and connection and connectivity for the Internet of Things. The stage 2, where the data sensing and collecting comes into place. Stage 3, where data transport and access get the data and provide and open the way for the analytics of the 4th stage. Then the data value defined by action, and regarding also depending on the IoT application, try to add to provide added value to the data for the application, and to improve all the business that comes on top, like the human value, the experiences, and this very applied technology in the healthcare, in the transport, in the energy, and in the smart farming, and all the very interesting applications, the very challenging applications of the IoT. So if I may, I can give you an example of smart farming, for example, of all this cycle, and how this paradigm matches on this application. So we have the devices that senses a farm. We have the drones that provides photos and high resolution images coming from the farm. And also we have some meteo stations that provide information about the weather. So we collect all these data. We have some aggregators. For example, The LoRaWAN protocol is very popular here. So we collect, we gather the data, and then we transport the data coming from the field to the cloud. So we have the gateways here. So the gateways forward the data to the cloud. In the cloud, we have the data analytics. So we filter the data, we analyze the data, we keep what is important, we annotate the data, and then the data comes into a value. So we have an added value, a data collection here, a data set, and we apply AI, machine learning, and based on the results of this analysis, we have a decision-making process, and we make decisions. For example, you can proceed to irrigation. You receive some suggestions of what you can do, or you also receive some warnings or recommendations about some anomalies, or about some estimated failures on the farms. So all of these things, it's a new market. It opens new opportunities for products and devices. Like, for example, in Terminate, as I mentioned before, we try to bring new devices of 3D glasses into play. So, you can imagine a farmer that wears 3D glasses, and he can see an augmented reality into place in a farm, in a livestock place, where in real time he can receive information about very important things like irrigation, like actions he can do in the farm, and recommendations about what he could do, and he also can see in real time the exact place of the action recommended. So that was a very tentative example of smart farming. Of course, other very interesting applications in next generation IT, like autonomous vehicle, smart factories, transportations exist as well. I will go through them later on. So the main 4 pillars of IoT at the current state has to do with the machine-to-machine communication. So here, 4G and 5G communications are very important, and the ongoing research on 6G communications as well. The RFID has to do with identification. Identification is quite important since a lot of devices, a lot of processes, and we need a very, let's say, effective way to identify the devices and the features behind. Then we extend the already existing wireless sensor network, where all the sensors, the aggregators, the meteo systems, and all the devices behind exist here. And also we have SCADA, and also the human to machine devices, and all the monitoring devices here, especially when talking about critical infrastructure like energy, healthcare, and transportation. So IoT involves not direct communication between the application and the physical layer, but involves cloud services and also some kind of network services here in order to provide flexibility, a new way and a new, more visible way to control and handle the devices behind, and of course, new market for new products. The RFID is more or less well known. So we have contactless smart cards in order to identify all the objects, the devices, some kind of static numbers, IDs. Also, IP version 6 here is used to identify all the objects. And given that the objects and the devices are getting larger and larger, so we need here an effective and cost-effective and something very efficient in terms of time serving in order to provide real-time identification without failures. Also, the SCADA is quite important. We deal a lot with our projects here in the university about SCADA systems, since all the industrial protocols are coming from an epoch and in times where, for example, the cybersecurity were not in the first priority in the agenda. So no authentication or other, protection schemes were designed. So many industrial protocols are open to cybersecurity and privacy gaps. So here is the main priority here is to protect and to provide trust to industrial applications, since by violating industrial applications, the impact of a cyber attack could be very, very large. And the well-known wireless sensor network involves from the traditional, autonomous and isolated wireless network for some local applications and uses to a major part of IoT, since now it composes the physical layer where all the devices, the interfaces, and all the connection options lies here. So by evolving from traditional IoT to next generation IoT, we have to consider that more than 3 billion new IoT devices will be added by 2023. So the scalability here becomes a major challenge for the next epoch. More than 75% of data will be processed outside of centralized data centers. That means that we need more AI, artificial intelligence, and more machine learning and more intelligence in general at the edge, close to the end user, close to the device. More than 90% of vehicles will be associated with IoT by 2030. So autonomous vehicle and all the vehicles, even when talking about drones and aerial vehicles, are coming to place, opening a new market where the systems, the control systems, the monitoring systems, and all the industrial systems that accompany all the autonomous vehicles, cars, etc., have to comply with very specific rules, especially in terms of cybersecurity, data handling, and privacy. So what we need in the next generation IoT domain? We need ultra-high data rates. We need reliability and coverage. We need more security, more protection in cybersecurity, more countermeasures here, and a new kind of trust. I mean, a new kind of trust environment between devices and between human and device. Also, scalability, adaptability, better cost efficiency are main terms that deal with next generation IoT. Without these terms and without ensuring that these terms will accompany all the physical and application layers in the next era, then we cannot provide an efficient new market for next generation IoT, a new business. We cannot provide a new business here. So if we can list very briefly the requirements of next generation IoT, we can see these terms as mentioned before. This is just a tentative list. To my perspective, I can say that end-to-end security, privacy, trust, reliability, and scalability maybe are the most important here regarding also our experience in the project, especially cybersecurity, trust, and privacy. So based on these remarks, let us see a bit of what are the main next generation IoT security challenges in the new landscape. So new devices, new connections, new interfaces also bring new gaps in the cybersecurity landscape. So for example, the autonomic control evolves in new industrial protocols, and these protocols should be tested, should be certified for passing specific tests and demonstrations regarding their power and their countermeasures against specific cybersecurity threats. So the security mechanisms have to address traditional and modern network attacks, but also to offer secure communication between IoT. Since all the new IoT devices are the main feature behind is that they are battery constrained, so they have some constraints on the power and on the process they can bring, they can bear. So we have to provide end-to-end security by having also the process elsewhere. So there is no possibility to have a heavy cybersecurity defense system in a light device. We have to provide some something else on the design of this ecosystem. In particular, if we divide the NG-IoT on specific layers like business support, communication, and perception, then we can also classify very, very specific and very focused cybersecurity threats. Like, for example, in communication layer, we have more or less well-known attacks like simple attacks, wormhole attacks, hello attack. Many of these attacks, focus on draining the battery or draining the energy, or to dissolve a bit the routing protocols. But if we can go up in the upper layers on the business layer, then social engineering, backdoor, buffer overflow attacks, etc., then all the ecosystem is jeopardized, could be jeopardized. And this is not something that could rely on the new, on the new area, on the new business. So we have to protect all the NG-IoT in a whole level. I mean, to provide end-to-end and holistic end-to-end cyber security protection by having tools in each of these layers. So examples of these NG-IoT countermeasures are starting from firewalls and honeypots, access controls, and intrusion detection systems, coming to SIAM tools and visual analytics, and then we can provide forensics at later stages, risk assessment tools, and some kind of blockchain trust level. So what is the status here is to bring some common tools that work properly, and then to advance them to provide more features and to apply a more holistic in a more holistic view by providing many levels of IoT, and for example, to provide also to allow also protection of not so well-known attacks, agnostic attacks, like IDS systems that could also detect anomalies not coming from the signature, but coming from real-time data analysis by, as we say, by having analysis of and deep inspection of packets. But of course, all of these things need process, need power, need memory. So let us see how all the involvement of 5G and all the involvement and the advancement in the network and the telecommunication level could also benefit on the next generation IoT. So what 5G is able to offer on the next NG IoT ecosystem. First of all, a more energy and more hours of operation. Then we can 5G could offer more scalability by providing more devices, for example, more devices connected to a base station. Also more capacity in order to increase, let's say, the land of operation and the landscape of operation. The highest throughput for providing and supporting more applications of NG-IoT. For example, in terms, we have a use case where we try to apply remote surgery in real time, where a doctor in a different country operates in real time in another country. So here we need very high throughput, and also we need very low latency, so as to support the haptics and all the feedback coming, for example, in the gloves of the doctor, so as to provide all these business in the highest level, by having also some thresholds, some minimum thresholds on the features of the telecommunication level of in terms of telecommunication. One very important thing that also comes together with the telecommunication involvement has to do with the edge computing. By considering edge computing, we mean that the intelligence goes down from the cloud to the device and to the end user. So it's I can say that edge computing and mobile edge computing, when we're talking about mobile devices, is something very, very crucial, something very important, and very on the top of the agenda, since this could allow more applications, more services, and also improvements on the ongoing services. For example, as I mentioned before, we can support not only one doctor to operate remotely, but 5 doctors or 10 doctors operating remotely in a surgery at the same time. So we can extend the services, and what is maybe what is the most important thing here is to reduce the latency. By reducing the latency, by having the process very close to the device, for example, what we have in Terminate, we have some accelerators that operate very close to the end user and very close to the sensors and the aggregators. So the accelerator runs all the AI, the machine learning, and the intelligence. So the latency between the sensors, the distance between the sensors and the aggregator is much closer than having all the training on the cloud, where the cloud could be, as you know, in a very distant level in another country, in another company. So reducing the latency here is of high priority. And new terms like edge and far edge comes into place, where long story short, we need to see far edge IoT smart devices where the devices themselves could support intelligence. So we can imagine that a sensor, a farming sensor that senses temperature, could also run AI, filter the data, and send only the useful data to the cloud or to the service. So we need to see all the physical infrastructure that the current time we talk is not aware of intelligence, to be in some level intelligence, so as to have data analytics at the bottom, at the device. So by having on the coming years, by having also the 6G, the expected 6G technologies, businesses, and new features, automated factories, smart health, personal experiences, automated vehicles, and more than a lot of other applications could be benefited, like automated factories. For example, require real-time data. So real-time, in general, real-time is a matter of a very long discussion, I can say. And since real-time, in practice, real-time means near real-time. So near real-time is also something that is a matter of many debates, but near real-time is not acceptable for many applications. So if we have a supply chain, we need real-time, not near real-time. So we need very specific minimum on the latency we can support all the devices if we need to have a scalable, a large supply chain in today's smart factories. Also, the edge processing related with all these devices, for example, in the supply chain, that could take some decisions, and not only to communicate with some other device to take the decision, but for these themselves to take the decisions and to process AI to have better results also in practice. Telecommunications is not enough. We need also some advancements and improvements also in the architecture. So one very promising solution to increase the visibility of the next generation IoT is SDN, by meaning that we decouple the control plane and the data plane. So what we can do in practice, we can have decisions real time without having reprogramming or reconfiguring all the systems. For example, we can have some routing rules by using OpenFlow, or before which is the next step of OpenFlow. So we can have some routing rules. We apply the routing rules, and at the current state, the routing rules are static. So if something happens in the network level, the routing rules cannot change in real time. By having OpenFlow and a new SDN layer in the network layer of the next generation IoT, we can have a real-time decision. So the routing rules could be dynamic and create new routing rules in real time without resetting the systems, without human interaction, without someone to, to monitor and play with the systems in the background. So it's quite important for us. For example, in cybersecurity, we can improve very much the cybersecurity level here. Since we can apply the IDS systems, the detection systems, we can have deep packet scanning. We can open, the TCP field and to read what is the application, what the application asks for, and what carries on, and then to apply rules, for example, to block traffic, or to to isolate some traces, or to apply new firewall rules real time. So it's quite important for the next generation IoT. And also here we can increase the visibility of the network. So we can have controllers where the controllers could control and monitor many devices at the same time, and could also monitor the traffic being carried out in all these devices, and to take real-time decisions on the network management and control level. So, for example, you can see here many promising and many popular controls like Open Daylight. We use the Open Daylight a lot here, ONOS and many more. And also NFV comes into place to provide flexibility. So SDN provides visibility, NFV provides flexibility. So we have all these virtual machines. We have all this flexibility to build up or scale down or scale up the systems behind. And various network functions and security and privacy functions could run in virtual network functions. So we can have a high-level architectural framework. Everything is abstracted, so we can play with all these systems based on the decisions of the lower levels. And also we can apply here visualization, and to exploit better all the 5G and later on the 6G resources. So we can have here optimized resource management of the telecommunication, cybersecurity, or process resources, and to exploit them better in order to support the physical layers. So when talking about artificial intelligence and machine learning, this is a very popular and very trendy these days, and this is quite true, since they could a lot to offer. They could offer a lot to the systems, and they could evolve much better the current state of IoT. I selected federated learning here since we use federated learning a lot, and I choose federated learning since it provides a lot of pros and better features than other methodologies like data privacy. So federated learning is applied to NG-IoT without violating the source and the privacy of the data. So we have local training, and the local training comes into the physical layer of, let's say, many domains. For example, we could have many let's say milk production domains or meat production domains. So local training exists here without exposing the data from one domain to another. Then we apply global models, where global models are trained based on the local models without exchanging real data, but they exchange only models, the trained models. And then we could exploit the data training and all the experience from different domains by improving a common goal. Like in this example, let's have a decision on the milk, on the quality of the milk, on the supply chain behind the milk, and at the end who is the beneficiary here is the end user. So we play with a lot of layers without exposing data towards improving and offering new possibilities, new potential to the end user. And what is important also here is that federated learning could exploit data coming from totally different domains. So we could have local data and to train a model coming from the transport layer, and at the same time we can have local data coming from the energy domain, and local data coming from the smart farming or forum farm, and all these things could be jointly train a global model that could be used in this or in other domains, in other topics. So federated learning opens, I could say that opens the way, paves the way to exploit data coming from many sources in a privacy preserving way to provide new opportunities to the end user. I could very shortly, I could also say some things about blockchain. Blockchain is also in top priority in the European Commission and in all industrial services. If we could define blockchain, we could say that it's a peer-to-peer distributed ledger forged by consensus combined with a system of smart contracts. In a more simple words, we can say that with blockchain, we built a trust environment. So we could have transactions, events, or whatever you can say what we can have here by recording all the history, by creating blocks, and by having the opportunity to going back to see what happened. So this opens the way for a trust environment. So everyone contributes to these blocks, so each action is recorded. Second, we can have a supply chain to record everything and to see backwards what happened in a failure. And the third one, we can have anything we need between members that are not trusted in a trust environment. So we have all this opportunity for creating smart contracts, and also to create, I'm sure that many of you are aware of all of these platforms, to have a way for exchanging not only events or transactions, but also money-related, let's say something very popular lately, money-related transaction. So we could create new systems of trust among members that are not aware, that are not known, that are not trusted already. And finally, let me also give you 6 main points about the trends. So where it goes, where all these new reference architecture goes. First, moving to the edge. So 8% of the processing coming from the cloud at this moment is coming from the cloud, and 20% at the edge. This should be changed. Second, we need to use meta operating systems on the edge and to start thinking about all these devices to be more dynamic, more active, more AI enabled. New data economy, which means that we have to maintain technology, to create technology in industrial environments where the things behind were static, threat, open to threats, and not so aware of AI, quite static. And we need also real-time safety critical systems for enhancing new applications, new sensitive applications like automotive, aerospace, and I can say here energy as well. Second, need for professionals. So we need here new kind of skills, new kind of knowledge. So we need skilled professional citizens for being aware and to be able to to cope with all these new technology topics. Also, we need a new kind of culture to support the digital transformation of businesses And of course, the new SMEs, the new enterprises, startups, and spin-offs could help a lot on this. Also, we need a federated cloud continuum. So we could keep the cloud services, but we need to enhance the cloud service with security, energy efficiency, portability, and all of these things with the help also of the effort being made at the edge. Fourth, we don't build on silos. We need open standards. We need open markets. We need new products that could exploit all these open standards, and also a new business that could exploit all these tools we have like blockchain to trust the systems and to control also their own data. Fifth, trust. So we need trusted IoT, trusted devices, trusted procedures, and trusted people that could handle all of these things. So certification is very important here to provide trusted environment, to encourage businesses to enter, the playground, to share data, to exchange data, and also to keep by exchanging data to keep also the sensitivity, to preserving the sensitivity and the privacy of the data. So we can play, for example, with models, not with the data itself. And about AI, of course, the analytics will play in the future at the edge. So we need a privacy design approach at the physical layer as well. We need personalized data-driven services, and also we need transparency here. For example, the latest EU regulation needs transparency on the AI regarding the gender, for example, the gender, the source of the data, and how all the process is followed to get the data, to train the data, and use the data. So for conclusions, you can see all these, all these pictures about the new area of NG-IoT. So, for example, you can see at the right that the devices could play a very active role in our lives in the near future. They could recommend us. They will speak to us, and they will ask things for us. I hope for our good. And also, since many of we have a lot of students here today, look that picture. I have concerns about this cybersecurity candidate. There's a candidate in the background. So the other guy asks anything in particular, and she responds, he's available. He's available means that why he didn't already be in another enterprise, another business. Cybersecurity and data analysis are two of the most missing disciplines, missing skills, and they are, at least to my perspective, the companies pay a lot for high-skilled cybersecurity experts and data analysis experts. So thank you so much for your attention. I would be very, very glad to respond to your questions or comments.
Thank you, Dr. Panayotis, for delivering a very interesting and thought-provoking session. This forum is open for questions now from audience members. If the audience members have any questions, they can post it in the chat box, or they can unmute themselves and ask them.
Thank you, Dr. Panayotis, for your nice lecture. I would like to ask you a question.
Yes, please. Yes, please. Yes. Thank you.
Actually, you know that nowadays IoT is also a bit of what I say, that a lot of work has been done. And nowadays we are thinking about related CRIoT, Cognitive Radio Internet of Things. Regarding CRIoT, how it could be helpful and how it could be able to solve the problem associated with IoT. Can you enlighten something about, or is it a feasible solution for smart city solution like the next generation technologies? If something, can you tell me?
Yeah. That's a good question. A major part of next generation IoT has to do with the telecommunication part. So as I mentioned before, what is important here is to reduce the latency, and second to increase the throughput. So the major question, as you said, is how we could support the next generation IoT ecosystem with telecommunication access, or with all the features that could be provided by licensed or not licensed telecommunication services. So I could see two options here. The first one has to do with light applications where we could use some kind of not licensed protocols like LoRaWAN or Zigbee or something like that. So you could set and you could use your own ecosystem without a license, without conflicting with other ecosystems. But in this way, you could provide light services. For example, smart farming, where the sensors transmit, not so much information, not so heavy information, is something quite appropriate for that kind of option. On the other hand, if you need to support heavy application like smart factories, or the example I mentioned before about remote surgery, then it's necessary to collaborate with some kind of licensed telecommunication services. So in that case, you need for sure some kind of 4G, 5G connection to support guarantee transmission or reception of data. So in that place, the cost is increased, and you could support all these services under a license. The landscape at this moment has these two options. Of course, the next generation IoT has a network level, but this network level is not something isolated. It depends on external, let's say, telecommunication services. So a next generation IoT evolves as 4G, 5G, and in general cellular telecommunication services evolves as well.
Thank you. Thanks a lot for discussing for this particular very important thing. Thanks a lot, Doctor.
You're very welcome.
Thank you, Dr. Yes, thank you, Dr. Panayoti. We were greatly honored to have you in this conference today. We have a small token of appreciation from the organizers of Gcaia. Shomin, sir. This is an award of appreciation from the organizers from Gcaia. Please accept it with sincere thanks.
Thank you so much. I would be very glad to receive it, and I'm very, very happy that I can see a lot of attenders and the very interesting discussions of the session. Thank you so much.
Thank you. Thank you.
With this, we reach the end of keynote speech sessions for today. Please join us again for the valedictory session at 5 p.m. Thanks to all those who joined today.